Let's get started with today's lecture. I told you arguably the hardest chapter in the book.
What?
Let me tell you now. Arguably the hardest chapter, not in the book, sorry, in first semester material that we'll cover. Because I'm going to have to introduce you to multivariable functions, and it's very hard to wrap your head around it the first time, and to keep track of when we're talking about the function in terms of one variable versus another variable. So we'll get to that, but before we jump into waves, let's do a quick recap of simple harmonic motion, remind ourselves of simple harmonic motion, and I want to stress a point that I didn't stress last lecture. But since it's been a little bit, let's remind ourselves of simple harmonic motion, what last section was all about. What is simple harmonic motion? Give it to me in a nutshell.
It's motion that can be described with a restoring force.
Yeah, there's going to be some restorative force, so it's some motion back and forth where there's always some sort of restorative force keeping it going. Our most common example was a weight tied to a spring, give it some initial bouncing back and forth and it will keep on going. Or the other one we did was a pendulum.
Yeah.
So I'm going to rework through the simple pendulum example. This time I'm going to do it in terms of torques rather than forces. But I'm going to solve the exact same problem I did for you last time. But what we showed last time is that if you've got some function where its position plus the second derivative of its position with respect to time can be written this way, where k is just some arbitrary constant, some constant, not arbitrary, but k some constant, then the solution to this differential equation is something of this form, where omega, your angular frequency, is the square root of whatever that constant is. That constant, when we were doing springs, was, what was it? K over m, where k was a spring constant and m was the mass of the object attached to it. And we'll see what it comes out to in the case where we got our simple pendulum, but we also did this last week. So if your equation satisfies this, or sorry, if you come across this differential equation, your solution is something of this form, where that omega is the square root of whatever constant you saw right there.
Yeah.
And what is omega in this context?
What's your angular frequency?
It's your angular frequency. Omega in this context is flat out defined to be, maybe scribble out up here, omega is defined to be 2 pi times whatever your frequency is.
Yeah, right there.
Okay. Yes, note that. Now, something that I did not do a good enough job stressing last week that I want to stress very heavily today. When we went back to uniform circular motion, what was omega?
Your angular velocity.
It was your angular speed.
Yeah.
What is your angular speed? That is your derivative of theta with respect to time. That is not 2 pi times frequency. That was your derivative of theta with respect to time.
Right.
This omega is very, 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 very different than this thing. They're very different quantities.
Yeah.
So, using the same variable in two completely different ways. In uniform circular motion, omega meant the change in your angular position with respect to time. When we're in the last two chapters, this chapter and last chapter, then our omega was simply 2 pi times your frequency. Two very different things. So I'm going to do the example with the simple pendulum also to help stress that point. So once again, let's have our simple pendulum. So here's the anchor point that's rotating around, got some mass tied at the end of the string. I take that mass and I let it go and it's going to swing back and forth. It's got gravity pulling down on it, tension in the string pulling up on it. The net force acting on it is just this mg sine of theta.
Yep.
So the net force, because this portion of gravity perfectly is going to cancel out tension. Otherwise the mass would be moving down or up, which it obviously isn't, it's tied to the string. And so it's just going to go that way from this restoring force due to gravity. So the net force is just equal to negative mg sine of theta. Why negative? Positive displacement. The force is always opposed to your displacement. Okay, so it's a restoring force, exactly what we expect with simple harmonic motion. So there's your net force. So what's your net torque? How do I get from a force to a torque?
You times it by your torque is your moment of inertia times your angular acceleration.
Well, that's our F equals ma version of it. But how do you get torque from a force?
Oh, you times it by the lever arm.
You times it by the length of your lever arm.
Yeah, that's right.
Right? Is it easier? Why is the handle at the end of the door?
Because it's easier to push at the end.
Because then you can generate more torque with the same force. The further away the force is, the bigger the torque.
Right.
The closer the force is, the smaller the torque. So torque is just your force times how far away the force is being applied. In this case, it's being applied at M. So here's our net torque. And the same way that the net force is also equal to mass times acceleration, so too is the net torque equal to your angular mass, moment of inertia, times your angular acceleration.
Yes.
Good so far?
Okay.
Okay. So now we have this equation. What is the moment of inertia of this object, this mass object, around this point?
It's the mass times L squared.
The mass times the distance squared, that's it.
Right.
That's how you calculate the moment of inertia for a point-like particle. We're pretending that that's all at one point.
Yeah.
We're not going to calculate the moment of inertia of some sphere some distance away. That would be a nightmare.
Isn't it just the same as the point at the center of mass of the object? Or am I taking it wrong?
Yes, in this case it would be. So in either case, treat it like a point-like mass. So your moment of inertia is just m times L squared, and then everything else is still the same. Good?
Yeah, okay.
We can cancel out one L from both sides, and we can cancel out the m's from both sides.
Okay.
And then I'm going to move the negative over here, so it's a sign.
Okay.
So this is missing one of its L's, and it's missing its m. This is missing its L and its m, and it's now positive because I moved it over there.
Okay.
Now, we have the sine of theta as opposed to theta. We remember our small angle approximation? If theta is smaller, much smaller than 1 radian, then it's roughly the same thing as sine of theta. Theta and sine of theta very closely resemble each other. And so we'll make that approximation and replace sine of theta with theta, and then I'll divide everything by L, just to get our constant in one place.
Why don't we just take the arc sine of it to get theta by itself?
Take the arc sine of it,
Or the inverse of sine.
then you're going to have the same problem. So our problem right now is we want, what is alpha? It's the second derivative of theta with respect to time.
Right.
So we need a theta and an alpha.
Right.
We have a theta in a trig function. If you took the arc sine or arc tangent, now you get this thing in a trig function. We need both of them outside of trig functions.
Got it.
So there's our approximation, dividing both sides by L. And so now what do we have? We have alpha plus some constant times theta equals 0. But what is alpha by definition? It's the second derivative of theta with respect to time. So I have the second derivative of this function with respect to time plus a constant times that function equals 0. That is of this exact same form.
Yeah.
Where there's our constant, and rather than an x representing our position function, we're talking about your angular position. And so what's the solution? The solution is going to be something of this form. Theta is equal to a times cosine omega t plus phi, where, what is that omega?
2 pi f.
It's the square root of whatever this constant was. It's also 2 pi f, so you can use that to figure out your frequency. But it's always related to this constant right here.
Yeah.
So there's your omega. What determines how fast the pendulum swings back and forth? Two things, the length and the acceleration of gravity.
Yeah.
A pendulum on the moon swings slower than a pendulum on Earth. A really long pendulum swings slower than a really short pendulum. That's what this tells us. Okay, and so, notice, here's our theta. Now, just for kicks and giggles, let's take the derivative of theta with respect to time. Here it is.
Where did you get?
I just took the derivative of this with respect to time.
Okay.
Just for kicks and giggles.
Okay.
Both those things. Okay.
Where did you get W from that?
The omega.
Omega.
Oh,
the chain rule.
chain rule. Derivative of the outside times the derivative of the inside. With respect to t, so multiply by that constant. Good?
Yeah.
Okay. Now notice, what is this? This is how your angular speed is changing as that pendulum swings, right? Your angular speed as the pendulum swings, it gets slower, 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 stops, speeds up, speeds up, speeds up, reaches some max point, slow, slow, stops. It's all over the place.
Yeah.
That's your angular speed. It's all over the place. Your omega is some constant.
Yes.
So this is what we mean by omega in last chapter and this chapter. Here's what we meant by omega when we were talking about uniform circular motion.
Why did he use the same symbol?
I tried to stress that at the beginning of last lecture to show you how they're related. I feel like I didn't do a good job explaining how they're also very different. That's why I wanted to come back with they're very different. And make sure that was crystal clear.
Okay. Good.
But why do we use the same symbol? Because of how this functions in periodic motion for how omega functioned in uniform circular motion. Notice in uniform circular motion, omega was a constant because it was uniform circular motion.
Got it.
Okay, so they were behaving very similar, but very different concepts.
Right.
Okay, so I think we've stressed that enough. Now, in preparation for today's material, I need to remind you about partial derivatives. And you gotta get comfortable with multivariable functions. A function in terms of more than one variable.
Isn't this Calc 3?
Calc 3, you focus on, yes, in a way this is Calc 3 material. That's when you would formally go over partial derivatives, so sure, yeah. Anyways, let's look at some simple multivariable function. Y is a function of x and t.
Yeah.
And it's just going to spit out the product of it.
Yeah.
Okay.
Good? Okay. Let's just calculate now the derivative of y with respect to t, the derivative of y with respect to x, the partial derivative of y with respect to t, and the partial derivative of y with respect to x, and make sure all four of these things make sense to us, and we understand how they're different.
Okay.
Okay, so with it being a multivariable function, one of the things that could potentially be the case is that x and t are somehow related to each other. Maybe x changes as t changes. They could somehow be related, and so we need to keep that fact in mind. So now let's start out with the full derivative. The derivative of y with respect to t, let's calculate that. How do you do that? Well, you got a product of two things, so you have to use your product rule. So it's the derivative of the first
Times the second.
multiplied by the second. So this would be the derivative of x with respect to t, we have no clue what that is, multiplied by the second, plus the derivative of the second, what's the derivative of t with respect to t? 1 multiplied by the first is the next second.
Okay.
There's a derivative of y with respect to t.
Okay.
Let's calculate the derivative of y with respect to x. The derivative of the first, what's the derivative of perfect, multiplied by the second, plus the derivative of the second, dt dx, whatever that is, multiplied by the first. Very different things.
Yeah.
Now let's calculate the partial derivative. What is the partial derivative of y with respect to t? That means pretend that x is a constant. Or in other words, if we were taking a slope of this function, I'm not sure if you can picture
Yeah.
a multivariable function. If we were to graph this thing out, we would need an x direction, a t direction, and then we have to plot our y up.
Yeah.
And so at origin, 0, 0, this would go up in the y direction, 0.
Yeah.
And if we went 1 in the t direction, 0 in the x direction, it would still be 0. So it would be 0 all along the x-axis, 0 all along the t-axis, and then it would curve up higher the further away from the axis you went.
Right.
Very hard to picture these things the first time you come across them.
You're saying the y.
Yes, what this function would look like if you tried to graph it, because you'd need 3 dimensions to graph it.
Mm-hmm.
You need 2 dimensions to graph a 1 variable function. You need 3 dimensions to graph a 2 variable function. Good?
Yes.
Okay, so what is the partial derivative of y with respect to t? That's saying if you take a slice of it where the x is constant, so take a slice of it where x is like equal to 5, see how the slope then is changing as t changes.
0. Nothing.
So you take a slice where your x isn't changing in that slice.
Right.
That's intuitively what it means. But calculating partial derivatives, actually much easier than calculating full derivatives.
Nice.
So you just treat x as though it's a constant. We're saying, what would the slope be if I held x constant and only allowed t to change?
So it'd just be t, right?
So it would just be, what's the derivative of that if x is a constant
Thanks.
with respect to t? It's just x.
Oh, with respect to t.
Good? And what's the derivative of this with respect to x if t were a constant? Just t. Good? Okay, that's it.
Nice.
So full derivatives, partial derivatives. Big difference between the two. Now we're ready to get into waves. For waves, let's think intuitively, what is a wave?
It's like a motion.
Movement of energy.
It's a movement of energy. That is a great way to describe it. Think about how strange it is if me and you were holding either ends of a rope. I can do work on the rope, moving it up and down, and it sends energy that way. Such a strange thing.
Yeah, that's right.
And it sends energy without moving any mass that way. All the mass just moves up and down as I wiggle that rope up and down, and energy is sent that way. The more you think about waves, the stranger they become.
I've never even thought about it.
Yeah.
And so a wave is a way of transporting energy without really transporting mass. The mass ends up back to where it started, but the energy gets sent. So you do work on one end of the rope, and then it gets transmitted down the rope, and now it can do work at the other end. And it sends that energy down. And that's why you need to do work to generate a wave, because it sends energy, work energy theory. Can't get anything for free. Good? So that's largely what we're going to think about, is what we call transverse waves. That's mostly what we're going to care about in this section. And that would be like me and you holding two ends of a rope, sending waves back and forth to each other. Transverse just meaning that the direction that the wave moves is perpendicular to the motion. Now that's not always the case. We can also have the wave move in the same direction that we have the motion. That would be called a longitudinal wave. And an example of that would be sound, hearing. Now I'm going to give you a complete lie, but it's a lie that gives you good intuition for how we send waves back and forth to each other. So ultimately, how do you generate a sound? Your vocal cords, you get them to move. They start whacking the air. So here I am with my vocal cord. Here's a bunch of air molecules in a room. These are going to be time shots of these air molecules. So this is time equal to 0, and then this is time equal to 1, So snapshots of these air molecules. And here I am with my vocal cord, and I'm just going to poke this atom whenever it gets close enough to me. This is going to be a little, not atom, but air molecule. A couple atoms together. I'm just going to poke it. So a second later, now that I gave that thing a poke, it's going to have moved forward and collided with this other air molecule. You see that?
Yeah.
Now they're going to collide. What's going to happen?
One goes back, one goes forward.
They're going to bounce apart.
Right.
You're saying they're elastic?
Yeah. They're going to collide and bounce apart.
Okay.
They're like little billiard balls. Okay? And so this one's going to bounce back towards me, and that one's going to bounce forward. And so the next moment, it's going to look something like this. Now remember, I'm right here. Every time I can reach it, I'm just going to poke it again. So when it comes back to me, I'm still talking. I'm still poking. I'm going to poke that air molecule again and knock it forward again. This one is going to collide with this one, and so it's going to bounce back. And this one got hit, so now it's going to move forward and bump into its next neighbor. And once again, after these collisions, that one bounces back, that one bounces forward, that one bounces forward, that one bounces back, and it looks like this. And now I'm going to poke that one again, so it's going to move forward. That one bounces to there, that one bounces to there, that one bounces to there, that one bounces forward. And once again, bounces back, and you keep doing this pattern. And what this creates is places where we have higher pressure. Intuitively, what's pressure? A lot of air molecules jammed together is a good way to think about it if they're moving at the same speed. And low pressure. And high pressure and low pressure. And when you see someone arc figure, you know, some guy right here, and he's screaming out, and you do your little sound waves like that, that's what that's meant to mark, is here's the high pressure areas and low pressure in between. That's your pictorial drawing of those sound waves. And so in this case, the air molecules are bouncing back and forth like this, into the next ones, into the next ones, into the next ones, until it's vibrating something in your ear, which then your brain is ultimately able to interpret, thank you, as a sound. So sound is a completely mental experience. Well, what you hear is.
Yeah.
But really, it's just atoms bouncing back and forth into each other all the way down. So you need some medium. All our mechanical waves, you need some medium to send the sound through. Whether it's the rope that you use or the atmosphere that you use. That's why you can't scream in outer space. There's no air to jiggle.
Right.
There's no such thing as sound in outer space.
Well, if the air leaves your mouth, wouldn't that count?
No, because it needs to jiggle the atmosphere all the way down. So even if I were to go and let out all that air, it's just going to spread out.
Yeah, but someone could hear it if it hits them, right?
No. 'cause
No, because it's going to start scattering.
There won't be a wave.
That would be like in the ocean, there's a tsunami traveling, that's a wave, and it keeps moving. If that ocean disappears, you don't get it anymore. I can't start a jiggle in a cup of water and then throw it at you
But you could
and have that wave hit you. Now the water would hit you, but it's no longer a wave. It's just,
So you still
water
hear the
scattering.
noise, it's just scattered.
no, you wouldn't hear anything.
It's just scattered.
Be some air.
You wouldn't hear anything. If you were extremely, extremely, extremely sensitive and had some very fine detectors, you might be able to detect some air atoms bouncing on them. But this motion is not happening anymore. There is not controlled chain reaction of things creating some uniform pattern of motion.
No.
As I know, you wouldn't hear anything. Because to hear, you need the jiggling back and forth.
Right.
You would just get dumped with wave atoms, or air atoms. So no screaming in space, no sound in space. Okay, so that's a longitudinal wave. And then if you were, I don't know, if you've ever like wiggled the edge of a swimming pool, that's like an above ground pool, and watched it create the waves there, then that's kind of a combination of both these things. If you were to put some dye on top of the water that you could watch, you see it actually moves in a circular motion, going back and forth. So both some forward motion and some up and down motion. So you can get combinations of the two. For this chapter, we are pretty much exclusively interested in transverse waves, basically thinking about sending them down a rope or down a string or something like that. And we'll have a lot more to say about longitudinal waves next section. Next section will be pretty much all about sound.
Wait, sorry, what is
Two rate-
the difference between those two again?
A longitudinal wave. So, what we're going to be tracking is the motion creating the wave. On a rope, then a piece of the rope generating the wave is moving up and down,
Yeah.
but the energy is going that way. When I do sound, now those atoms are moving back, those air molecules are moving back and forth, and the energy is going that way.
Okay.
So longitudinal means it's in the same direction that the wave is going. The motion of the particles transmitting the wave is in the same direction that the wave is moving. Transverse waves is the motion of the particles generating the wave is perpendicular to.
Are like infrared and gamma and radio all transversal? Transverse?
Are those all transversal waves? I don't know if for it to be a transverse wave, it also has to be a mechanical wave. I'm not sure the classification. But it is the case that when you do work perpendicular, it sends the wave perpendicular to the motion of work. That is true. If I take my electron and I jiggle it up and down, my emitted electromagnetic wave will be perpendicular to that. So it's transverse. I'm not sure if it's technically a transverse wave. I'm not sure if this is a special classification of a mechanical wave. Because an electromagnetic wave is not a mechanical wave. It does not need a medium to travel through. It can travel through empty space. So that's the only thing why I'm saying I'm not positive. I would guess yes.
Do we know how Wow.
Yes, that's what we mean by, in general, radiation. It's something that's able to radiate through empty space.
Doesn't have to be a photon to do that though.
Now, obviously, actual particles can.
And that's what solar flares are? It's
A solar flare?
No,
No, it's a ton. I mean, it's going to have a bunch of electromagnetic radiation in there, but it's also going to have just a ton of
Yes.
protons and electrons, some actual things that have matter at rest speed, have mass at rest speed, going as well. So lots of charged particles together with, yes, some electromagnetic radiation. But, so for this chapter, we are pretty much interested in these mechanical transverse waves. Pretty much waves that you can generate with a string or a rope. That's what we'll pretty much assume we're talking about from here on out.
Okay.
The other assumption that we are going to make is that the velocity of the waves that we are talking about is constant in the material.
How is that possible?
It's the way it typically is, unless you're in extraordinary circumstances.
You're saying the velocity of a single particle on the wave is constant?
No, sorry, the rate at which the wave moves. So you and I are holding a rope at either end. If we keep the tension the same and the rope is uniform mass density, once I start that wave going, it's going to continue with that same velocity, the actual movement of the wave through the rope. And that's what we'll mean by the velocity of the wave. So the velocity of the wave has, I'm not going to say it has nothing to do, but it is not how fast the rope is moving up and down. It's how fast the bumps are moving along the rope.
How do you change it? How do you make the velocity go faster or slower?
Well, we'll come up with a formula for velocity, and we'll see that it's a property of, you have intuition for this if you've ever played with it with a friend before. How do you get your bump to speed up? How do you get your wave to go faster? You pull tight, and the harder you pull, the faster it travels. And if you loosen it, then the wave slows down. If you loosen it enough, the wave won't even get to you.
Yeah.
And then the other thing that makes it harder to send a wave, if I give you a really fat rope versus a thin rope, which one's easier to send a wave through? The thin one. So we'll see that the harder you pull, the more tension it's under, then the faster the velocity, and then the denser the rope is, the slower the velocity. And we'll derive that. But so we will be assuming that with the fixed material under a fixed amount of tension, that the velocity is pretty much constant. So draw pictures of the waves we're going to be talking about and draw it in two different ways, because now our waves are going to be multivariable functions. And here's the part that terrifies me the most. So one way I can draw my wave is I can draw it as a function of x. So here I am, and I'm sending waves down to a friend. Me and him are holding two ends of a rope.
Yeah.
You can take a picture of that. So your flash goes off, you take a picture of how it looks at a single instant of time. And here's what that might look like. So my hand happened to be at the highest point generating the wave at the time that you took the picture. And here's what it looks like at that frozen instant of time. So at my position at x equal to 0, it was at its max height. Over here 2 meters, it was level with where it was before we started making waves. Over here at 4 meters, it's down some.
Yeah.
So what we mean by wavelength is when you take a picture, take a snapshot in time, what is the difference, what is the distance between these crests?
Isn't that period?
Or what is the distance between these troughs? This is not period. Period is a time. This is a distance. We are in the x direction, and here's where I'm terrified. Now the other thing you could do is ignore the whole rope and just watch the piece in my hand. And so it starts out right here, then I go down, then I go up, then I go down, then I go up, and I go down. And now you could graph that. So this is graphing what one piece in my hand is doing with respect to time.
Okay.
And now the time, from when it was right here to when it gets back up, that's the period.
Okay. Got it.
So when you're graphing it with respect to time, the distance between your crests is the period. When you're taking a snapshot of it, then the distance between your crests is the wavelength.
Okay.
Snapshot in time.
Snapshot in time, whereas looking at just a single piece of the rope, the piece in my hand,
Okay.
as it changes with time.
Or any other point along the rope, I assume.
Or any other point along the rope. So this is looking at our wave at some particular x equal to x naught. This is looking at our wave at some particular time equal to time t naught.
How would you graph it if you added time to that first graph?
Now you need a multivariable. You'd have to use 3 dimensions.
You would?
Not necessarily. Can't you just show?
This is how it looks at one instant of time. Go forward a little bit. Okay, now it might look something like this. So here it is after a little bit further into the future. And a little bit further into the future, it'd be shifted a little bit more, a little bit more. If I tried to graph all those in 2 dimensions, I'm just coloring this whole thing in.
Well, you can pick
I have to have a t dimension and an x dimension, and say for any combination of x and t, here's what the height is. And then that would look like a surface. And that's also not very intuitive. It's usually easier for us to just think about it, take a snapshot in time, or focus on one portion of the rope, one atom of the rope over time, and break it up into looking at one axis at a time rather than trying to combine these things.
Right.
I guess it doesn't really matter. Because you can just figure out at any time what it looks like.
You can figure out, that's what we need to come up with an equation. We need to come up with our equation for this wave so that at any time and at any position along the wave, you can tell me exactly how high it is. That's the equation we need to come up with. And that's our goal for the next section of the class.
Which is why they use y.
So they're using y. Y is how much it's shifted away from its equilibrium position. And notice that y here and y here are the exact same thing. This is how high it shifted away from its equilibrium position with respect to time. This is how high it shifted away from its equilibrium position with respect to space. So the amplitude of this wave and the amplitude of this wave will be identical.
Okay.
This is watching me shift the thing up and down in my hand, just that one atom, this chalk piece.
Yeah.
This one is take a picture of what the wave looks like at one instant in time. And so now it's looking at the entire rope, but just that single instant in time. This is looking at one piece of the rope for all of time.
Yeah.
Okay, going back and forth between that way of thinking is what's going to hurt, and why this is so hard. If you can easily do that, then this section is not going to be bad at all. Okay, so now let's start coming up with this equation. One of our first assumptions that we're going to make is that our function, when I start generating our wave, I'm going to do so with simple harmonic motion. So my hand is going to be moving in simple harmonic motion.
Which is consistent.
Well, that's just the way I'm going to generate it. So whether it's my hand going back and forth, or maybe we tie, a string to a weight on a spring, and we have that go back and forth to generate our wave, whatever.
Well, it doesn't need to be like that, does it? Just gets way harder.
You can get waves that are not generated that way. We're going to start out with waves generated that way, because it's the easiest wave to start thinking about.
Are we going to talk about the other ones?
Like a
Ish.
Okay.
You'll see the ish that I mean.
Okay.
Okay, so starting out with a simple harmonic motion driven wave, meaning that the way we're constructing the wave is we're moving up and down with simple harmonic motion. Good so far? So what does that mean? So if I am generating the wave in my hand, and my hand's moving through simple harmonic motion, then that means whatever the function is for our entire wave, when it describes the portion of the rope in my hand, it has to use a simple harmonic motion function. It has to use one of these functions. These are our functions for simple harmonic motion. So we're trying to come up with our equation for a wave. We're trying to figure out y of xt equals, and we're trying to figure out what that should be. We're trying to come up with some function where at any position, any time, you can figure out exactly what the height of the rope at that time, at that position, would be. How far away from its equilibrium position it would be.
Isn't that a? Doesn't a and y equal the same thing?
No! Look at it. My y here is a. This is a, the amplitude. But then right here, that's not the amplitude, it's way smaller. Here it's 0.
Duh. Yeah.
So we're trying to come up with some function so that if I were to freeze time and go to that exact position and look at the rope, then you can tell me how high from its equilibrium that chunk of the rope would be at that time.
Basically.
That's the function we're trying to come up with.
Yeah.
Making sense? Now, since our wave, we're assuming it's driven by simple harmonic motion, then the portion of the rope that's in my hand has to follow simple harmonic motion. So it has to satisfy an equation like this. Now we're going to call the portion of the rope in my hand at position, what's its x coordinate, the rope in my hand?
0.
0. That's what we're going to call 0. So y, whatever this function is, when you set the x to 0, and the t is whatever it is, it has to look something like this. Now you might be saying, well, what about the phase angle? For the sake of simplicity, we are always going to call time 0 when the position 0 is at its max. So I'm agreeing with you right now that so I get my wave going, I'm going to start my stopwatch, and time 0 will always be when my wave's at the top, my hand's at the top.
That's convenient.
Yeah, it's going to keep the math a bit simpler so we don't have to keep chasing this term all over the place, this phase shift term. So that's something we're agreeing to do now to keep everything simple. All your homework problems and all the example problems will always be generated this way. And we'll always call time 0 when it's at its peak, and x0 the portion in your hand. Good? And so, for the portion in my hand, that's at position 0, but the time is changing as it goes. That function is going to look like this.
Okay.
So whatever the x is, when you set to 0, it has to look like this for whatever our overall function is.
Okay.
With me so far? Okay. Now, once again, we're getting started, so I got my wave going. Time 0 is when my hand is at the start and we start our stopwatch. So at time 0, here's what the wave looks like with respect to x. So this is taking a picture of it at an instant in time.
Okay.
Good? Mm-hmm. Now, I'm going to go forward a little bit of time, t1 seconds later. Here's now what the wave looks like, because it changed as time went by.
Yeah.
Someone drawing all sorts of stuff. So it changed as time went by. I am now going to say, so here was the top of the wave in my hand. So I'm moving my arm back and forth. We start our stopwatch as my hand's at the top and my hand goes down some. The top of the wave moved forward some. So this point on the wave, following the wave now, moved here. And I may call its position x1. So x1 is wherever the top of the wave is now at some future time. That same exact wave though, following the same wave. So this one can't now be over here. I'm saying x1 is the top of that wave that I had in my hand at time 0.
Okay.
So at t1, wherever that wave moved, we're now going to call its position x1.
Wherever that energy moved.
Wherever that wave moved, wherever the energy moved, for that same crest. You with me so far?
Yeah.
Okay. So here it is at time 0. Here it is at time t1. Maybe a second later or whatever. Okay. Our position now, x1, how far away from me is that going to be? Well, that's just going to be the velocity of the wave, however fast the wave is moving this way, because this wave is now moving this way with some velocity v, times t1, however many seconds later it is.
Yeah.
We good?
Mm-hmm.
So, x1, how far ahead that point is after t1 seconds, is just v times t1. Solving for t1 is just x1 over v. With me so far?
Mm-hmm. And so velocity is time 1 over x?
Yeah. No, velocity is x1 over t1. Because distance over time gives you velocity. Okay. Now the part I'm worried about saying. Now notice that from this point onwards, x1, t1, this position, behaves the exact same thing as this point, x0, t0 did. From this point onwards.
From crest to crest, that was it.
Well, now, if we go forward along these waves, it's going to be identical.
Yeah.
So in other words, I'm saying, now from this position, go forward 1 second. Whatever x looks like is what this looks like 1 second forward from time t0. This one, from time t1, 1 second forward, will look the exact same as this one did 1 second forward from time t equal to 0. Or, if you look at this point at time t1, x1, and you look 1 meter ahead of it, whatever the rope looks like, will be exactly what it looks like 1 meter ahead of this at time t0, x0. So our function at time 0, or at x0 time t, is going to look identical to how this function looks at x1, starting from time t plus t1.
Those are the same graph, right? It's just position.
These are the same wave at 2 different times.
Okay.
So what my function looks like at x0 for any time is now going to be what this function, what the function looks like starting at x1 from any time after t1. In other words, how this function behaves at this point is identical to how it behaves at this point, starting from some amount of time forward, which we're calling t1. So how this one behaves at time t1 is exactly how this behaves at time t1 is exactly how this behaves at time t0.
Okay.
How our x equal to 0 behaves here at time t equals 0 is identical how position x1 behaves here at time equal to t1.
Okay.
And going forward any time, they will now mirror each other.
Yeah. Okay, see.
That's what I'm trying to say here. So whatever the x1 is, however it functions, it needs to make this function behave the same way that this one did at time 0. When you plug in x1 t1 to this.
I see.
And so it has to cancel out the t. Maybe just jump to the conclusion here. So here is going to be our general function now, where x over b is, just to write this in general, what is x? X is equal to b times t. Or in other words, t is equal to x over b.
Yeah.
Notice that x over b is going to be the time when x is a peak here.
Okay.
That's going to be the same as the time. And so this is going to cancel out to 0. And so it's now going to behave the exact same way here at x1 t1 as it did at 0, 0 here. So here is our function. It's like your x determines how much you shift the function. That's another way to think about it. This function from this point onwards is the exact same as this function from this point onwards. It's just shifted over some to the right. And this is how much you shifted over to the right. How much you shifted over to the right? The amount of time it would take for the top of the wave to get there. Maybe that's a better way to say it. And the subtraction is a shift to the right, the same way an addition is a shift to the left. You've seen this 100 times when you think about like a parabola. When I do x minus 2 squared, what is that? That's a parabola shifted 2 units to the right. Why is it shifted to the right? Because you have to plug in positive 2 to get your 0 point, to get your bottom. Similarly, that's a parabola shifted 2 units to the left. So, same thinking if that helps. I don't know, trying to connect the intuition here. So, notice that this behaves identical to this when x is 0. So, when x is 0, we knew our function had to look like this. Notice that's exactly what you get when you plug 0 in for this. When you plug in 0 for x, this whole term goes to 0, and you just get a cosine omega t. Similar, look at what happens when you plug in 0t to this. It's going to be the exact same thing that you get when you plug in x1, t plus t1 here. Let's write that out just to make it very clear. So I'm going to write this out, plugging it in here.
Okay.
So what do we get? We're going to get a times cosine, it really matters as the argument part, omega times, for t, what are we plugging in? T plus t1. And for x, what are we plugging in? x1. What is, sorry, and parentheses. What is x1 over b? It's just t1. And so you get t1 minus t1. And they cancel out, which makes it identical to what we got when we plugged in 0. It makes that identical to this. So say this one more time. What is x1? It is where the crest of the wave is now after time t1 seconds. And so since we had a crest at 0, 0, x1 by definition is where the crest is at time t1. And so the function has to be equal at x1 t1 to what it was at 0, 0. So when I plug in 0, 0 to this, and I plug in x1 t1 to this, I get the exact same thing. More generally, this function behaves from time t1 onwards, identical to how this function behaved from time t equal to 0 onwards.
Yeah.
Right here, onwards, is identical to this one onwards, which is what we were saying here, for any forward time going forward. And now this works in general for any x. We don't have to use x1, t1 there. We can now use x in general and t in general. Another way to say that is every portion of the wave now undergoes simple harmonic motion. So I make one portion undergo simple harmonic motion in my hand. every portion of the wave from there on out is undergoing the same exact simple harmonic motion once the waves have time to propagate. Thank you. Does that make sense? I know it's hard to think about it, right? Positions at different times.
Yeah.
I went back and forth 4 different times thinking, should I graph this in terms of time and do a jump forward in position, or should I graph it in terms of position and do a jump forward in time? I wasn't sure which one would be easier for you guys to follow.
Need a position and time.
Yeah, what it actually looks like if you take a picture of it, jumping forward in time. Okay, so here is our equation for our wave that you'll be using over and over again. The same way that you use this equation for simple harmonic motion, here's what you'll be using for these waves, these transverse waves. There's the equation.
It's so tough.
So tough? Now we have this equation written out 4 different ways, depending on what's most convenient for your use case. So, here's what we just came up with.
Wait,
Why is
isn't
X
that's X over V minus T, not T minus X?
Oh, thank you. Perfect. Now, they choose to do this. Not sure the reason for choosing to do this, but this just comes from trig. Cosine of negative theta is just equal to cosine of theta. So you can multiply your argument by negative and it doesn't change anything.
Huh?
So multiplying by negative just switches the order. Cosine of negative theta is equal to cosine of theta because cosine is a even function. It's true for all even functions.
Oh, okay.
It's the same reason that if your function is x squared, then f of negative 2 is the same thing as f of 2. It's an even function.
Did we go over that in geometry or was that straight math?
I don't know.
Screw that.
Went over it somewhere.
Sure.
We did talk about even functions in discrete math, I think.
Yes. We
Did
talked
we
about
have proven
even,
that's even?
even functions and odd functions in calculus.
Oh, we did in calculus
Oh,
for
we
sure.
did calculus.
Yeah. Okay. Anyways,
We have unity.
so going from here to here, we're just using the fact that it's a cosine function. So you can multiply the argument by negative and it doesn't change anything.
Okay.
So you actually won't see this one. Sorry. This is the one you'll see. So I drew the 4 that you'll see down right here. These are the 4 that you'll see.
And they mean the same thing.
And they're all different ways of representing the exact same equation. So we'll go over each of them. So first off, how did we get from what we came up with to this? Well, since it's a cosine, you can multiply the argument by negative, which when you multiply a difference by negative, it just swaps.
And why would you ever want that?
Well, because that's where your book's written, and so...
So it doesn't really matter.
No, you could work with it this way and it wouldn't change anything.
Okay.
They choose to have it written this way. Now, this, honestly, this is the way it's most commonly written and the one you'll use over and over again. Or at least the one I always use. I don't remember all these.
Is that a lambda?
Yes.
What's that?
Wavelength. T is your period. That's your length between, your distance between crests when you're doing it with respect to time. Lambda is your distance between crests when you're taking a snapshot picture.
And they
You go over
measure
that-
the same thing.
You go over that note right there?
No!
Well, they don't measure the same thing. They're going to be the same number.
No!
What?
No. They're not the same.
Okay.
Period is the time it takes my hand to wiggle up and down as I'm making the waves along the rope. That's period. Lambda would be, as I'm making the waves on the rope, you actually go and measure, here's the top of one, if you were able to freeze it, take a picture of the wave as it looks like, and then go measure from the top of one wave to the top of another wave. And so I could have a period of like half a second, and my wavelength could be like 2 meters.
Did you go over that note right there? Next to your, the V equals lambda over T, and lambda times F.
Oh, I don't know, I think I said we're going to assume velocity is a constant. Okay, let's make sense of both these. That is good. Thank you for saying that. So, velocity, how fast your wave is traveling, is going to be your wavelength divided by time, your period, that it takes to get a wavelength.
Okay. That makes sense.
So the period is the time it takes my hand to go down and back up. If I'm back up, then that means I've generated a whole wavelength. And so now look at the next crest to my hand. And that's going to be wavelength. And the time it took me to do that is 1 period. Period is a time, lambda is a wavelength.
Nice.
Or is a distance, I mean. Now, by definition, frequency is just a reciprocal of period. And so you can also do it as velocity is equal to lambda times frequency, which is probably the way I'll most often write the velocity. This is the most natural way to write the velocity of a wave.
Isn't frequency the same thing as period?
No, they're the inverses of each other.
There's a
Frequency is how many rotations, it's how many cycles per second.
Cycle.
Period is a time. It's how long it takes me to generate a cycle.
it's
Frequency is how many cycles I generate every second.
so period.
So if I am moving my hand back and forth, and it takes me a half a second to go up and down, then my period is half a second. My frequency is 2 hertz, because I'm doing it twice every second.
I see. Yeah, that makes sense.
Okay. Very different. They're reciprocals of each other, but very closely related.
Yeah.
This is most often the way that I'm going to write the functions, or the wave's velocity. It's the common way that's written.
Why did we choose a lambda here?
Because it's a Greek letter that we haven't used very much. I have no idea.
Same
Okay.
reason we
Drop
use
a line.
omega twice.
Just another letter.
Alright.
So yes, lambda will mean wavelength going forward. Okay, so we covered that note. We have our equation for the wave. This will give you its displacement from equilibrium at any position at any time. That's what it gives you.
Why are we looking specifically for y?
We need an equation that describes our wave.
Can it be x or t?
Y is in terms of x and t.
Yeah, but isn't t in terms of
So
y?
you're asking for an equation of x in terms of y and t?
I need some equation that describes my entire wave. So I need to not only know what my wave looks like right now, I also need to know what is it going to look like in a second, in 2 seconds, in 3 seconds. This enables me to plot it out for any position, for any time you care about. I can tell you exactly how high it looks. And I can regenerate any wave you want. You want a picture of it at a specific time, at 2 seconds, plug in 2 for t, and that will tell you what to graph now at for time 2 seconds.
So what would this look like on a 3D graph?
It would look like a surface, your x direction that way, your time direction that way, at any direction or at any time, at any position, then you would follow those coordinates and it would be plotted up some distance, up or down.
So like it's just
And so it would look like a waved out surface.
Sick.
And then any slice of it in the x direction would be saying at a specific point, or sorry, any slice in the t direction would be fix the time. And so that's telling you what a specific point looks like with respect to time. And a slice in the x direction, same thing the other way.
Right.
And that's what these would look like. This is a slice in the t direction. Oh, both these are slices in the t direction.
Yeah.
But here's one where it's a slice in the t direction and one where it's a slice in the x direction. Okay, anyways. So we got this equation. Here it is. And you know what all these symbols are. Omega, that's your angular frequency.
Is that 2 pi?
X is a position, T is a position. 2 pi.
Times omega.
Omega, that is this definition of omega right here, yes.
Yeah. So it's
What's
just
That
the
is
other one?
2 pi times the frequency. We're done with the other omega. All right, we're done talking about derivative of theta with respect to time.
Okay.
We're not talking about that anymore.
But what about your other omega?
what you mean the square root of p over L?
This one,
Yeah.
this was the same as this omega. It's what it was for this particular problem. So you can figure out the angular frequency for this particular problem and figure out the frequency for that particular problem and the period for that particular problem. Because once you have the frequency and period are just reciprocal of each other. So if you have angular frequency, divided by 2 pi gives you the frequency. Flip its reciprocal gives you the period.
Okay.
Okay, so that omega, yes, it's very similar to that omega, how that was behaving there.
Okay.
Okay, so omega, angular frequency. If you have the frequency, you know how to get your angular frequency. Multiply by 2 pi. X, just your x position along the wave. T, just however many seconds we are after time 0, where we start our stopwatch. And V is the velocity of the wave going forward. Now, so far we haven't come up with the equation to figure out the velocity of the wave. We'll do that.
Doesn't V equal wave over t period?
Perfect. That is one way that you could do it. If you know your lambda,
It's on your second board.
and you know your, yes, if you know your lambda and you know your period, then you can calculate your velocity. And that's one way to do it.
So we do know how.
It's also,
If you have lambda here.
Is
Yes.
lambda, oh.
lambda's your, yeah.
Okay. So now, I'm going to show you how we get this version of the equation.
You just substitute your omega.
Omega is just 2 pi times the frequency. There you go.
What's the point?
Is that all I did there?
Yeah, what is the point of that?
Okay, so there you go. You have the frequency, you can't really remember what omega is, well, now you're saved. Okay, there's one equation. Now we're going to take this equation, focus on this inner part. That's right there. I'm just going to distribute, remember that's not an f as in a function, that's frequency.
Yeah,
Okay, so we're multiplying it by this thing.
yeah.
So when you distribute it to that inner part, just looking at the inner part, then that's going to be f times x. Down here we're going to have f times v.
Which is your t.
What? Why do you put lambda there?
I don't know.
Wait, it's your v.
Because the f, sorry. F just goes to the numerator. Why am I trying to multiply to the bottom? Very stupid thing to do. V is simply the same thing as lambda times frequency. Okay, sorry.
Okay.
Very dumb moment. Okay, so multiply the f to the x. There it is. V is the same thing as lambda times frequency. And then you gotta multiply the f to the time.
And the f.
And f is just a reciprocal of period.
And the f's cancel out over there.
And the frequencies cancel out there. So now, that's what we have written here, just making that substitution.
Oh.
So now, it's saying 2 pi, you have x position divided by wavelength minus time divided by period. And you can see how there's something natural about that. Put your lengths together and your times together in the equation.
And why are they manipulating it like this?
Just for whatever's useful for your particular problem and what you know.
Oh, so just giving in terms of what you know.
Yes.
Like arcane math equations.
Oh, that's,
Okay,
that's pretty easy.
now we're going to manipulate this one. And before we do this, we have to introduce you to something that maybe you come across before, maybe not, called the wave number.
What?
The wave number.
The number of waves per second.
It's the number of waves you can fit in 2 pi, and that's all it is. It's a k is literally 2 pi divided by your wavelength. It's called your wave number. It's something that you would have potentially seen in classes prior to this. It's somewhat common to do this, but there's its exact definition.
So okay,
It's the number of wavelengths you can fit in 2 pi.
Sorry.
If your wavelength is exactly 2 pi, then your wave number is 1. If your wavelength were pi, then your wave number would
Oh,
be
it's clear.
2.
2 waves in 1.
2 wavelengths in 2 pi. It's just how many wavelengths you can fit in 2 pi.
Why did they use k for that? They have a whole Greek alphabet.
Yeah, so k is coming up again. And now from here on out, here's what k means. It's not your spring constant.
Friction.
It's not your arbitrary constant. K now is going to be the wave number going forward.
Okay.
Coefficient.
So k, what's k? It's how many wavelengths you can fit in 2 pi.
That's insane.
And 2 pi radians.
2 pi radians, correct.
So one circle.
Okay.
Yeah.
I'd rather think about 2 pi as a cycle here than a circle.
Right, then.
But also understand that you're doing a wavelength.
Wait, 2 pi is a period, right?
No, that's why I didn't want to say that. 2 pi is not the period. The period is the period. It's the time it takes for me to wiggle my hand up and down. That's the period.
So what's
2 pi is 2 times 3.14159, da, 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 that's 2 pi. It's a number.
okay?
Okay, so wavelength is just 2 pi divided by,
Okay.
or your wave number is how many wavelengths you can fit in 2 pi.
Okay.
Alright, that's all it is. Now with that, we're going to take this inside. Oh, another thing to note before we do this. What does 2 pi over your period equal then?
Your. That's That's 2 pi frequency, right?
Period is just a reciprocal over frequency,
So it's omega.
and so it's just omega.
Okay.
Okay, so now notice when I distribute my 2 pi in here, if I distribute my 2 pi in there, 2 pi over lambda is
Lambda.
Okay.
k, and 2 pi over period is omega.
2 pi over period is omega.
2 pi over period is omega.
2 pi.
2 pi over lambda is k.
Oh.
And so this is the way that you are mostly going to be working with this. This is the most natural way to have it written, as strange as that seems.
That makes sense.
You're going to think
Just
about it
that
as,
stupid K.
yeah, wave number times x minus omega times t.
And your x just should be.
And every time I have to use it for any example problem, here's the one I'm just going to start with, and I'm not even going to remember these other ones.
X is displacement, isn't that?
X is the position you care about, t is the time you care about. This gives you the height of the wave at that position, at that time, from its displacement.
From its displacement.
From its equilibrium position, sorry. How high or how low it is.
That's your y.
That's your y.
Oh, okay.
That's what this, right, this whole thing is equal to y of xt. Alright, so yes, that's how you calculate your y.
Fire.
Cool.
Good?
Can we do a concrete example?
Before we do velocity,
Why would you do this? I guess.
Are we gonna do a concrete example after we do velocity?
I was going to do examples after we finish velocity.
Okay.
Okay.
Okay. So, oh, move camera. Let me just see if I can get that column in case we need to make reference to it. Okay, I see everything. Okay, velocity of the wave. Since we are mostly going to be using this equation, the constants we're going to have most of the time are k and omega. So it's going to be most convenient now to have velocity in terms of k and omega. So what is velocity? Well, it's the wavelength times frequency. What is lambda
Wavelength.
in terms of k? Just swap those two. It's 2 pi over k.
Yep.
And frequency is just 2 pi times omega. What did I do wrong?
Did you do something wrong?
Yeah.
What? I mean, that makes total sense. What do you mean? There should be 4 pi squared of omega over k, shouldn't it?
Omega is 2 pi times the frequency. Frequency is equal to omega over 2 pi. Okay. Frequency is equal to omega over 2 pi. And now the 2 pi's cancel out. Okay.
Why
Yes,
is it?
you're right. Okay.
Omega is equal to 2 pi times the frequency.
Yep.
So frequency is omega divided by 2 pi. So frequency is omega divided by 2 pi. Lambda is 2 pi over k. 2 pi's go out and you get omega over k. So now when we use this version of the equation for our wave, we can now calculate its velocity as just omega over k.
Why is it just specific to that one equation?
I just told you, of all these equations, the one we most likely are going to use the most is this one.
Yeah, but doesn't that B solve for all?
You can always solve for velocity this way, that's perfectly fine. I'm just saying now, let's get it in terms of omega and k. Because odds are most of the time we're going to figure out what those values are. So now this helps us hurry up and figure out the velocity without having to refigure it out using frequency and wavelength,
Oh, so
which you could. So it's just a convenience thing. Okay, now let's think some relativity. Not like that, just Galileo.
Oh.
So let's say that here I am generating a wave, and you are going to walk at the exact same speed that the wave is traveling.
Uh-huh.
Relative to you, what does a wave look like it's doing?
Stay still.
walk-
Staying still right there with you. So whatever phase the wave is in, if you happen to be walking right next to a part that happened to be a trough, relative to you, the phase is always going to be a trough. If you happen to be walking towards a point that was always zero, relative to you, that point is always zero.
Yep.
So if you are walking next to the wave at the exact same velocity that the wave is traveling, then its phase, its inner part here that determines what portion of the cycle it's in, is always going to be a constant. You with me? Okay. So from your reference frame, the phase is always going to be some constant. And that constant is going to determine if it's at its max, if it's at its min, or somewhere in between. Okay. So then, let's take the derivative with respect to time of this thing. Okay? So,
It's a constant.
taking the derivative of this with respect to time, k times x is just going to be k times dx dt, because k is just a constant.
Okay.
And now take the derivative of this with respect to time. The constant's still just constant. What's the derivative of t with respect to t? 1. So now, that's just going to leave us at omega. Move the omega to the other side and divide by k. And dx dt is equal to omega over k. What is dx dt?
Velocity.
Velocity. So velocity is equal to omega over k. It's coming out another way.
Q.
Okay.
So, just two different ways of coming up with the velocity, trying to help get some intuition for thinking about these things. Good?
You're saying these two, or
Well, I showed you that velocity is equal to omega over k. Coming at it one way, I showed it to you another way just using this exact definition.
oh,
So, just helping establish intuition for it. Different ways you can come up with it. Okay, now let's talk about the wave equation, which is not the equation of our wave. The equation of our wave happens to satisfy what physicists call the wave equation. The wave equation is something that shows up in physics
Like
throughout. It's very common.
Schrodinger's wave equation?
If you were to go take physics 3, which would be, what do they call it? Wave mechanics.
I thought it was modern physics.
You can also do that. That's called modern physics. It goes multiple ways, but you can go take a waves specific course. Okay. But the point is, for waves in general, they happen to satisfy. Do they all? If you come across an equation, okay, same way that we had simple harmonic motion. If you came across an equation that satisfied this, then you had simple harmonic motion, where the square root of that constant dictated your angular frequency. With me so far? It turns out, if you now have a y function, and it's going to have to be a multivariable function in terms of x and t, that satisfies this equation, then you have a wave propagation where the velocity is going to be, take whatever this constant is, and then 1 over your velocity squared is whatever that constant is right there that shows up.
what do you mean by satisfied?
Okay.
You plug it, so I'm going to show you that our equation satisfies what we call the wave equation. And that's what I'm going to show you.
What does that even mean? What
It's a solution to it. So if I say x squared plus 2 equals 6, what is a solution to that? X equal to 2 is a solution to that. X equal to 3 is not a solution to that.
There's only one solution.
No.
Well, 2 and negative 2 in this case. There's only 2 numbers that satisfy this. When you were looking at this, what functions can I find such that when you take the second derivative of them with respect to time, then add it to this function, there's some constant difference between them. Multiplying a constant by your initial function, you can get 0 out of it. What functions satisfy that?
A lot of them.
And the functions that satisfy it are this form. We did that when we did simple harmonic motion. Things of this form satisfy that equation. So now, what function can you find such that when you take its second partial derivative with respect to x, that's equal to some constant times its second derivative with respect to its second partial derivative with respect to t.
That's a weird constant.
Well, who cares what the constant is? The point is, if the second partial derivative with respect to x is the exact same thing as your second partial derivative with respect to t, differing by only a constant, then what you have is a wave. And it satisfies this wave equation, and its velocity you can calculate from whatever the constant happened to be there.
Why is that the wave equation? Why is that specific equation the wave equation?
Because things that satisfy it are waves with that velocity. The same way that things that satisfy this are things in simple harmonic motion.
Okay.
Okay, so we're going to show that this satisfies the wave equation.
Okay.
Good? Alright. So here's the equation that we came up with, and we're going to use, I told you I'm always and forever now going to use this version of it. The one with the wave number and omega. Now we're going to take its partial derivative with respect to t, which means treat x like a constant.
Okay.
So taking its partial derivative with respect to t, what's the derivative of cosine?
Negative sign.
Negative sine. And then we have to multiply it when we do our chain rule, multiply it by negative omega.
Yeah.
The negatives cancel out, and so you just get omega times that whole thing, but just replacing the cosine with the sine.
Yep.
Now, this is how our functions y is varying with respect to t. So this is giving you its velocity in the y direction at that specific point x. That's another way that you can think about what this equation gives you.
Okay.
How fast that particular piece, so if x is 0, then that's talking about the piece directly in my hand, and how fast it's moving up and down as a function of time. Good? Okay. Now, once again, take the derivative, the partial derivative of that with respect to t. That's going to do this. What's the derivative of sine? Cosine. And then chain rules. We got to bring a negative omega out.
Yep.
Which gives you a negative omega squared. Now, notice, once again, we have a negative omega squared times, what is this piece right here? That's just our initial y function, our initial position function. And so you get negative omega squared y is equal to a times y. So your acceleration is just your position times some constant. You with me? Well, that's crazy. Doesn't that mean that it satisfies simple harmonic motion? Well, yeah, obviously, because that's how we generate the wave. But you can see, okay, so this thing satisfies simple harmonic motion.
Okay.
No surprise there, no shocker there, but just notice how that's coming out of the math. Okay, continuing on our merry way. Now let's take the partial derivative of this with respect to x. So this time we're going to treat t as a constant.
Okay.
So when we do that, what's the derivative of cosine? Negative sine. And then the derivative of the inside just brings out a k.
Yeah.
Good? Take the partial derivative now of this with respect to x. Once again, derivative of sine is just cosine, and bring out a k, once again, for the chain rule. And surprise, surprise, the second derivative with respect to, the second partial derivative with respect to x is once again just a function in terms of the initial position function.
Right.
Yeah.
And so, if you want to view this as a function of time, or if you view it as a function of position, both of those satisfy simple harmonic motion. You get that same type of relationship. No surprises there. Intuitively, what does the partial derivative of y with respect to x give you? If I were to plug in x and t, it's going to give you the slope of the function at that time and at that position. So if our time here was 2 seconds, and our position was 2 meters, that means here I am generating it at 2 seconds. Take a picture. Go to the 2 meter mark, measure the slope of the wave at that position, and that's what this gives you. Good? And then if this one gives you the slope, what does this one give you? Your concavity. Whether it's concave up or concave down.
You know how that works.
Good?
Yeah.
Okay. And now finally, let's take the quotient of these two. So I'm going to do this one divided by this one.
Why? Why are we doing that?
I'm going to show it satisfies the wave equation.
Oh,
So when I do this one divided by this one,
we can do that. I guess we can. Yeah.
writing that right here, what do we notice goes out? Notice that
Y
these,
equals
look at the easy version of them. So I'm doing this over this.
The y goes out.
The y goes out and the negatives go out, so I get omega squared over k squared,
Oh, velocity
which is velocity squared.
squared. So we need a 1 over velocity squared.
Yeah, so now if I put the velocity over here with this one, and I move this over here, then you get this one.
Yep.
You see it? The v squared goes downstairs over here, this comes upstairs over here.
Okay.
Gives you this equation.
Okay.
So it satisfies the wave equation, where velocity squared happened to be omega squared over k squared. Okay, so this is a solution to the wave equation, where what is the v squared? Well, it's that. Same way that you would come up with solutions to this, where your constant would be whatever. In this case,
Square root of k. Oh, yeah.
so the same way that the constant would give you your angular frequency there, your constant is giving you the speed of the wave here.
Okay.
Good?
The constant k here is your wave number.
K is your wave number, W is your angular frequency.
Okay.
And you'll get used to the wave number as you go through this chapter. I know it's completely out of the blue and seems completely arbitrary at first. Okay, so there's the crazy part. Now we can relax a little after this derivation. Okay, so in this derivation now, I'm going to derive the velocity of the wave now as a property of the system.
What do you mean?
What do I mean here? It means that if you were to tell me how tight you're pulling the rope, and you were to tell me the density of the rope, I should now be able to figure out the speed at which your waves will go back and forth.
So you're relating height and density to speed.
The tension and the density to the speed.
Yes.
Okay, so far we've been showing how velocity is related to other constants,
Yep.
right? Now we're going to see how it's related to the actual physical materials that you use and the physical system that you set up.
So we should be able to use these other constants to find out the material properties of the rope if we.
Correct. Or vice versa, you know the material properties of the rope, and so you're able to figure out what these other constants should be.
Okay.
Okay, so let's set up the scenario. Here I am holding the end of a rope attached to the wall.
Okay.
And I'm holding it, applying some force F, applying a tension on the rope. And now I'm going to start wiggling up and down to start generating my wave. So going from here to here, this is sometime t seconds later. I've now lifted the rope. That lift is propagating throughout. Obviously, when I lift this end, it doesn't instantaneously lift over there. Right? And so it's got to travel through the rope. So here it is, traveling through the rope. P is the point that my wave has traveled to so far, as I'm generating my first wave here. Good so far?
Yeah.
Okay. Now, the rope in my hand isn't suddenly moving that way, so I'm maintaining the same pull this way.
Yeah.
But I'm also pulling it up. So the force I'm now applying, which I'm going to call T here, it still has the same component of F in the x direction, canceling out what the wall is doing. My rope's not going anywhere. But it also has some extra F in the y direction, which it has to, because obviously, what was our intuition for what a wave does?
Moves energy.
Moves energy. So I got to do work. This is my force doing work now.
Yeah.
This force isn't doing any work. This is the force that's going to be doing work. That component. Good? Okay. So here I am. I'm going to be lifting up the rope. This whole rope is going to be moving up with some velocity, v sub y. And then the wave is moving forward with some velocity, v. Don't confuse those two.
Good.
Since it's some time t seconds later, the amount I've lifted it is just the velocity I'm moving it up with times t. And this distance is the velocity the wave's traveling times t.
Yep.
Good with all those?
Yeah, that makes sense.
Okay. Now let's just do a quick reminder. Going back, your change in momentum with respect to time gives you a force. What's momentum? Maybe start with there. Let's remind ourselves what's momentum if you don't remember.
Mass times,
Mass times velocity.
yeah.
Take the derivative of that with respect to time. What do you get?
Force.
You get mass times acceleration, which is a force. Okay, that's where that's coming from. So your change in momentum with respect to time gives you a force, or in other words, you have to apply a force to get a change in momentum is another way you can think about it. So, if we integrate a force with respect to time, what do we get? A change in momentum.
Yes.
So in our particular case, notice the force, this rope is moving upwards. So it now has some momentum. That momentum was generated from this force, F sub y. So F sub y times t is going to be equal to m times vy, where m is the mass of the portion of the rope that's moving. So m, I'm not sure how to write this. What is m equal to? Oh, I forgot to specify. Our rope, we know it has density mu. So our mass is just going to be mu times,
Volume.
no, v times t. What's density? It's your mass per unit length. What portion of the rope do I have moving? This portion. So that's the portion with,
Your mass is your density times your velocity, or volume.
this is your density per unit length, not your density per unit volume. When I talk about a heavy rope, I say it has a mass of 1 kilogram per meter or whatever. So this is kilograms per meter. I tell you my rope has this many kilograms per meter. Say my rope has 2 kilograms per meter, and I have 10 meters of the rope. How much does my rope weigh? Or how much mass does my rope have? 20 kilograms. So this is kilograms per unit of length. Times it by multiplying by the length. What length of the rope do I have moving?
V times t.
This length, which is just v times t. So that is the length of the rope I have moving.
You can't just go do mu times volume of the rope.
Well, if mu, we don't do volume of a rope. We do length of a rope.
Makes it weight.
Why can't you do volume?
You can, I just don't want to calculate the volume of a rope.
That's how we always do.
No.
So,
When we deal with ropes, we treat them as one-dimensional objects. When we deal with surfaces, we treat them as two-dimensional objects. When we deal with
boring.
volumes, we treat
Solids.
solids, thank you. We treat them as three-dimensional objects.
Okay.
So, mu here is how many kilograms per meter the rope has. So if I have that many kilograms per meter, and I have this many meters of rope, I have this many kilograms of rope, which is the mass of my rope. Good? Okay. I'm surprised no one's pointing this out. What are you talking about? This is the length of the rope. Not this.
We haven't gotten there.
Isn't this the length of my rope?
Yeah.
Not this?
Correct.
I mean, I don't see how that would be straight when you're generating a wave anyways. Usually it's kind of...
Yeah.
And the answer is, that's the length of my rope now because we increased the tension on it, and so we stretched it out some. But it used to be like this. And this was our density for the unstretched rope.
You're stretching the rope.
Yeah, because
What?
this is a blown up version of how we're getting it started, right? When I first start lifting the rope.
Oh, so your
Oh, this is a very
density is
long
decreased in proportion to how much you're...
And so your density increases proportional to how much you stretched it, but it's still the same amount of mass that there was when the rope was unstretched right there. Is the point.
How does your density change?
rope.
Okay, it doesn't. Here it is. You're okay with that? I'm okay with that. Let's go for it. Let's not go out into the weeds over a technicality.
Stretching your rope.
Couldn't you also do it as the hypotenuse of that triangle though for your length? Or is that not-
Our density was for the unstretched rope.
Oh.
And this stretched portion has the exact same amount of mass, that this unstretched portion had.
Oh, that's why.
And so we calculate the mass of this unstretched portion, and we're assuming that in the act of stretching it, we didn't change the mass.
But you're
This is a very dangerous assumption we're making. Stretching a rope doesn't change its mass. That's what we're assuming.
Makes sense.
Yes, it does. Okay, so there's our mass. Good with the mass.
Yeah.
And it's moving up with some velocity v sub y. We know how to calculate that v sub y. That's going to be the same thing that this was. That's what we mean by v sub y. How fast the particles move up in the y direction. So
Okay.
we know the v sub y, and we now know the mass, which can enable us, or sorry, there's an expression for the mass. Overstatement. The point now is that using this relationship, f sub y times t, that f sub y times t is going to give me exactly my momentum of my rope moving up. That's my last item. Good? Okay, next, let's talk about similar triangles. How's the best way to say this? Maybe you could just see it. Notice that this rise, f of y, over this run, f, is exactly the same as this rise over this run.
You're saying ratios?
Yes, those ratios are the same. The ratio of this to this is exactly the same as the ratio of this to this.
Well, doesn't seem obvious.
Because my tension is along the same direction as my rope.
Okay.
Makes sense.
I mean, they also have similar angles, right?
Yes, that's the point of what we're saying here, is that this angle and this angle are the same.
Yeah.
Good?
Yeah, that makes sense.
Okay, so my f of y over my f is the same thing as my rise in the y direction over my run in the x direction. Good? Okay, now I'm going to cancel out my t top and bottom and put that v over there and that f over here.
Okay.
Okay, now my substitution for v of y.
Yeah.
From this equation, v of y is equal to, v sub y is equal to, f of y t divided by m. Maybe I didn't even need to write it, you can just see it.
Yeah.
So I'm going to make that substitution right here. Oh wait, no, I'm going to substitute my f of y, sorry. Sorry, substitute for my f of y, so divide by t. And so f of y is equal to m times v of y over t.
Okay.
And then we still have our same v. So I've substituted my f of y.
Yeah.
Okay, so that's how I got from this equation to this equation, substituting my f of y from this relationship right here. We're good with that?
Mm-hmm.
Divide both sides by
Log v of
V of y.
v sub y.
v of y.
So divide both sides by v sub y, and I'm also substituting in what I know my mass is.
Okay.
So v of y's go out, and my mass is the same thing as mu times v times
Your
t.
t goes out? Or do you,
It's going to go out now. You're going to see I'm going to be able to cancel out my t's now, and I have 2v, so it's going to be a v squared. And put the mu over there. So v squared, v times v is my v squared, put the mu over here and t's cancel out. Maybe just cross out the t's, you can see those cancel out. Put the mu over there. V squared is equal to f over mu, or finally, our velocity is equal to the square root of force over our density of our rope.
And the force here is your
Is the tension you had in the rope.
and your y force as well.
No.
No.
Notice that it does not depend upon your y force. My y force would help determine how quickly I send waves down.
Oh.
My y force is related to my up-down motion. This force is only the force we have in the x direction. So it's the force we have in the x direction that determines how fast the wave travels down the rope.
so with the same force and the same, or with the same tension, the same density, going like this, your wave travels the same velocities going like this.
Perfect. So if you maintain the same force going up and down really quick compared to doing it slowly, does not change how fast the wave goes down the rope.
It just changes actually?
It's going to change the frequency.
The wavelength.
It's going to change how much energy goes down the rope. The amount of energy you're putting into the system, the amount of work you're doing on your end of the rope, but how fast the wave actually travels is just a consequence of the properties of the rope. It's kind of like jumping ahead. We'll see this for sound. Sound waves travel at a constant.
Yeah.
Me screaming louder doesn't make the sound travel faster. How fast the sound travels is going to be a property of the medium it's moving through. How fast the wave in the rope travels is going to be a property of the medium it's moving through. Just matters the tension that the medium's under and the density.
You're saying low pitch and high pitch travel same speed?
For sounds, yes. And low frequencies and high frequencies down the rope travel at the same rate.
Does
That's
that
what this is saying.
mean that sound travels differently at ocean level than it does up here?
Yes.
Yes, it just travels slower and farther.
And it also means that sound travels different in different gases in general. Change the gas makeup, it's going to change your sound.
Yes.
Which you've seen tons of times talking through helium, and the sound goes faster,
Yeah, to speak.
That's why it's
causing the waves to be bunched. Well, we'll talk about it when we get to it, but helium essentially makes it sound like higher frequencies. Argon essentially makes it sound like lower frequencies.
Yep.
But anyways, so it's just a property of the medium it's traveling through. Now, we just did this for sending a wave down a rope. It turns out, in general, this is always the case. And so, good intuition to have. The velocity that a wave moves is always and forever going to be proportional to the restoring force. Notice that it's the tension that you're putting in the rope that's trying to straighten it out again. So your tension in the rope is acting as your restoring force.
Whoa. Okay.
Okay.
Right?
Yeah.
And then, divided by your inertia, whatever's resisting the movement.
Which is the mass of the density.
Which in our case, it's the density of the rope. Not the mass of the rope, the density of the rope. Notice that sending a wave down 1 meter of rope is the same as sending it down 2 meters of rope. You don't really care how long the rope is, you care about the thickness of the rope. That's what makes it harder or easier to send the wave down.
Right. Okay.
Okay. So here's what it's always going to be in general, so that's good intuition to have in your back pocket for just when you're thinking about waves in general.
Okay.
The sound will always be proportional to whatever's trying to restore the force, that's going to make it velocity higher, and whatever's resisting the movement to propagate the wave, that's what's going to make it go slower.
Okay.
Good?
That's the fifth way to find V.
Alright, so with that, let's jump through as many example problems as we can before moving forward.
There's 5 different ways to solve it.
Go on.
5 different ways. There's probably, there's always going to be a lot of ways to solve for everything because everything's always related to each other. All these related quantities.
That can be simple. Back in my day.
Back in your day? What was it like back in your day?
Simple.
Simple. That's all I know.
Simple harmonic motion.
That was back in the day, back when we were just doing simple harmonic motion.
That really-
Okay, that's plenty of space. All right, let's go ahead and start jumping through a bunch of these examples.
Excellent.
Okay.
Converted to the tablet gang.
That's so strange.
Yeah, way easier than trying to read off of my laptop.
What about the projector? No projector do it?
No, I'm not going to set the projector. Just going to hurry up and read it. The only reason for the projector was so I could easily read it.
Right.
You can read it in your own book if you want to follow along. All right. Sound waves are longitudinal waves in the air. The speed of a sound wave depends upon the temperature at 20 degrees Celsius. We know that the speed of our sound wave is equal to 344 meters per second.
What page are you on?
We are on, in terms of the book page, 476. In terms of the PDF page, 502.
Okay.
Okay. If I have a sound wave and I know that its frequency is 262 hertz, not sure if that's high frequency or low frequency,
No.
our job is to try and figure out, that's approximately the frequency of the middle C on the piano. So that's middle C. Then our job is to find the wavelength. So what's lambda? So I know the velocity, I know the frequency, what's lambda? Well, always and forever, what's our velocity equation for a wave? Almost always we think about it as frequency times lambda, which is probably the first way I have it written over there. So how do I find lambda? I take velocity and I divide by the frequency.
So it's pretty simple.
So very simple. So you do that, let me think. I think that comes out to 1.31 meters.
Yeah.
Good? There's example problem 1. One that'll probably keep you up at night. Alright, let's see. So our next one. Your cousin holds one end of a clothesline taut and wiggles it up and down in a sinusoidal wave with frequency. So we know our frequency is equal to 2 hertz. Just significant figures here. 2.00 hertz. Alright, so there's a frequency that he's moving up and down with. And he's using an amplitude of 0.075 meters. So he's moving it up and down 7.5 centimeters. We know that the velocity that it's moving down this rope with, the velocity of the wave, is equal to 12.0 meters per second. At time t equal to 0, we have our rope at its maximum positive displacement. Assume that no wave bounces back from the far end.
You can do that.
Huh?
You can do that.
Yes.
What?
This was something we'll talk about that when we get to the next portion of the lecture. Wave bouncing back. But yes, it can.
Isn't that how they use noise cancellation, like Apple?
Wow.
Sure. Yes. Similar concept. Destructive interference is what they're after there, but
Yeah.
anyways, so find the wave amplitude, A. We already have a wave amplitude that was given to us in the problem. So there's that. The angular frequency, omega. What's omega? It's equal to 2 pi times the frequency. So take that, multiply it by 2 pi, and there we go. So 4 pi is our omega. Let's see what else they want us to find. Find the period t. Our period is just a reciprocal of our frequency. So that is going to be 0.500 seconds.
The wavelength.
Find the wavelength. How do we get our wavelength?
It is
The way I always think about wavelength is frequency times wavelength gives me velocity. So our wavelength has to be
Velocity times frequency.
velocity divided by frequency, which in our case is
6.
6.0 meters.
Repeat.
Yeah. You have 2.
Yeah, because this one only has 2. Oh, that's 3. And that's 3. The amplitude was the only one with 2. You're right. So 6.00 meters.
So,
Okay. Okay, we found everything. Part B. Write a wave function describing the wave. So that means actually write out the function. So y of x t is equal to a. What's our a? 0.075
Cosine.
times the cosine
Okay.
of k. What is k? It's our wave number. It's 2 pi divided by
T.
6.
the wavelength. So 2 pi divided by 6, or pi over 3. Pi over 3, 3.15 divided 1.05. So 1.05 is going to be our k,
Okay.
times x minus omega. Omega is 4 pi. So what's that going to come out to? Just look at theirs.
12.6.
12.6. 12.6 t. And there we go. There's our wave equation. Good?
What about your time? Oh.
Part C. Write equations for the displacement as a function of time of Throcky's end of the clothesline, and then at the point x equal to 3. So they're saying, here's what it is for any position at any time. What would it be just at the end that I'm holding at position x equal to 0? So if we're going to force x to be 0, and so now y is the only thing changing, that's saying what is it going to look like for the piece in my hand?
0.075 7
So that's going to be
cosine
y at 0t
negative 12.6.
is just going to be 0.075 times the cosine of plugging in 0 for x gets rid of that term.
Negative.
And so 12.6t. You can say negative 12.6t. Remember, cosine of a negative argument is just cosine of that argument.
Yeah.
So that's probably a slightly better way to write it.
Yeah.
And since it's not a function, you could just write this as y of t if you want. Because now we fixed the x. We chose a specific position on the string that we're going to talk about. And now they said also do it at position 3.
Okay.
So doing it at position 3, that would be y at 3t. And what's that going to be equal to? The exact same thing, 0.075 times cosine of, we'll do the negative here, so I'll write my 12.6t first and then do subtract 3 when we multiply by this.
Yeah, 3.15.
So 3.15.
1.5.
Okay, so there we go. And once again, you don't have to put the 3 there if you don't want. Just make sure when you say this, maybe call that y at 0 and y at 3 to make it clear what we were doing. So there we go. So there's example 2. And if I remember right, example 4 builds on example 2. So I'm going to jump to example 4, and then we'll come look at example 3. So example 4. Oh, that uses power, and we haven't done power yet. Okay, so we'll keep that up since that was example 3. Or example 2. Remind ourselves that this was the information for example 2, because we'll have to use that for 4. So this was example 2. And then I'll scribble example 3 up in the space we have here. So for example 3, one end of a 2 kilogram rope is tied to a support at the top of a mine shaft, 80 meters deep, and the rope is stretched taut by a 20 kilogram box. Okay, so we got our rope hanging here. It's fixed at one end, and then at this end, we've got a 20 kilogram weight. The rope, we know, they said it's 80 meters long?
Yes, 80 for now.
80 meters long is how long the rope is. We'll just put 80 like that. So what is the density of the rope? They told us that the total rope weighs 2 kilograms. 2 kilograms over 80 meters means our density of our rope is 1 over 40 kilograms per meter. Good so far? What is the... Now our person down in the mine shaft, right, they're right here, they're going to wiggle this end of the rope. So what is the tension on that end of the rope before they're back and forth wiggling? So we're assuming they're just going to wiggle it back and forth.
It's just the weight of the rope.
But it's just going to be the weight, not of the rope, but of the weight tied to the end of the rope.
Yeah.
So the F that we care about in this case is going to be equal to just 20 G, mg. Notice if they were wiggling this end of the rope, this wave is technically going to speed up as it goes. A little bit. Because the tension in the rope changes as you go higher up.
Why?
Oh.
Because up here you have to hold the weight of the whole rope plus that. If you were here, you just have to hold up that weight.
Oh, but
So tension increases as you go up, but we just want the speed at the bottom.
yeah, but we're massless rope.
No, this is a 2 kilogram rope. So we know that the mass of the rope is equal to 2 kilograms. That's how we were able to figure out its density.
Do we have a function that describes how the tension changes over the length of the rope?
It's just a linear change.
Oh. Okay.
Right? Because the tension at the top is just going to be 22G. The tension in the middle is going to be 21G. The tension at the bottom is 20G. Just changes linearly with the rope. Okay, but all we care about is the velocity at the bottom of the rope now. So what is the speed? So our miner, he wiggles the rope at the bottom. What's the speed at which it travels up the rope?
Okay.
Starting at the bottom. And that is just going to be equal to the square root of F over mu. That's all it is. And so in our particular case, plug in 20 times 9.8 and divide it by 1/40th, and then take the square root. And let's see, do all that math in my head really quick, and it comes out to 88.5 meters per second.
So you mentioned the tension changes over the rope, so the speed of the wave increases, right?
Yeah, so you could calculate the speed at the top, and that would just be V, put T here for top. If you wanted to plug it into your calculator and figure it out, that would just be 22G divided by 1/40th.
So,
Or take 22 times 9.8 times 40, take its square root.
could we write a function for the velocity that tells you the velocity at any point along the rope?
Sure. You would just have to break it up, make a function for where you are here, going up to 80 at the top.
Got
Okay, so there's the velocity of it. Let's see what else I wanted. The geologist at the bottom wiggles the rope sideways. What is the speed what is the speed of a transverse wave on the rope? B, if a point on the rope is in transverse simple harmonic motion with frequency 2 Hertz, how many cycles of the wave are there in the rope? Okay, so now, let's say that our guy down here is wiggling it back and forth at a frequency of exactly 2 Hertz. Which means it's taking him a half a second to go back and forth as he's wiggling it.
That's pretty hard.
So now as he's doing that, it's going to send a wave up this rope. How many full waves is he going to be able to see in the rope?
Through the entire rope?
Yeah, so he can see the whole rope.
Right.
How many waves can he actually see at one point? How many waves can we fit in that 80 meters? How many wavelengths?
So what's the wave number? Is the question?
Well, so what's the wavelength is
Wavelength divided by
our question. So what is wavelength equal to?
Waves.
If we have our velocity, how do we get wavelength?
Velocity is equal to wavelength times frequency.
V over F.
V over F. So 88.5 divided by 2. So it's going to be 44.2 or 44.3 depending on how it rounded. In this case, it'll come out to 44.3 meters. Now, how many of those can you see in 80 meters? Not quite 2. So if I have 80 meters of rope, a wavelength is 44.3. And so how many of my waves am I going to see? I'm going to see almost 2, not quite 2.
1.98.
1.98? That seems high.
1.81.
1.81 sounds right. And you just make up a number, just see if I'll write it.
Close enough.
Okay, so there's that one. All right, so before we can do the next example, we'll have to do a bit more lecture. For power now. How much power we send through these waves, how much, in a sense, energy. Yeah, we can do break. All right, let's
We're doing rank.
dive back in now. So the next section we're covering is energy in waves. And really what we're going to calculate is the power that you put into a wave. The amount of joules per second, or watts, you put into the wave. That's what we're going to be more interested in. So we're calling it the energy, but we're not calculating energy directly. We're going to calculate the amount of energy per unit time. That's what we really care about.
Why not the energy?
Why not the energy directly?
Yeah.
We care more about, it's going to be kind of related to the frequency. Higher energy is going to be higher frequency. Or sorry, not higher energy per second. It's the energy per second that we care about, which kind of describes how you're generating the wave. Not really the total amount of energy you put into the wave over however much time. Say I put a ton of energy into the wave, but I did that over 2 years.
Right.
Versus doing that same amount of energy in a second or whatever.
Right.
So that's what we really care about is the power, not necessarily the energy. We care about the energy per unit second, per period, per cycle. Okay. So setting up the exact same scenario that we had over there. So here I'm holding one end of the rope. I'm pulling up on the end of the rope. It's tied to a wall at some other end. There's some force F of tension in the rope. Here's our point P. I didn't label that. But exactly the same as before. We're just going to calculate the power. Oh, I decided not to do P so that you won't get confused because we're using P for power. So I'll call this a point, I don't know, That's just going to, forget that. Who cares what the point's called? Okay. But good with our picture? Do you need to look at it for a second to remind yourself of anything? Same exact picture. Okay. Now let's remind ourselves what power is. What is power?
Work over time.
It's work over time. It's the amount of work you're doing per unit time. So power is just work over time. Another way you can think about it is force times velocity. Where does the force times velocity come from? Well, how do you calculate work?
It's
Force
work
over
over-
Force times displacement. And then displacement over time gives you a velocity.
Yeah.
So however you want to think about it, both of those work. So now, if I want to come up with a function that is telling me the amount of power I'm generating in my wave at any position, at any time, it's going to be, notice that which force is putting power into it. Notice that this F is not putting power into it. It's my one going up and down that's actually doing the work, but that's putting power into it. So this F here that we're talking about to generate our power is going to be this F sub y. That makes sense? Which is potentially a function of x and t. Maybe it's changing as I'm going back and forth, which it most likely is, right? And then also our velocity, the velocity we care about is the velocity in the same direction as our work that we're doing. Because that's where the direction our displacement's in.
Okay.
Good so far?
Mhm.
Okay, so we know that calculating our power at any position at any time is going to look something like this. We've got to figure out what these functions are that give it to us. Well, we already know this one. It's really this f sub y that we got to figure out now. Our v sub y we've already calculated, and that's just the partial derivative of y with respect to time. So our v sub y is equal to the partial derivative of y with respect to time, where y is the equation describing our wave. Good?
Is it a T?
Yeah, sorry. Getting lazy. Partial derivative of y with respect to t.
Okay.
That's what we mean by this. And so really it's this f sub y portion that we got to figure out, and then we'll have our power function. Good? Now, exactly what we said before. Well, not exactly what we said before, similar to what we said before. But notice that f sub y over f, that's kind of like the rise over run.
Yeah.
And so that gives us, that's going to be the same as the slope of our function right here.
Mhm.
You with me?
Yep.
Now it's not exactly the slope of our function, because f sub y over f is going to be a positive number, whereas our slope is negative. So same ratio, but just a negative.
Wait. How is that?
Notice that before we were using this over this, but really that VT's in the negative direction. And we were treating it as a positive number. Okay. But if you want to think about it as going from here to here, and you want to think about that as positive, well, now we're actually going down, not up.
Right.
So however you want to think about it, but notice that this number over this number is the same as the slope of this line, except for the slope of this line is negative, not positive. However you see that.
Right.
Okay. Now, how do you get the slope? Well, that's your partial derivative of y with respect to x. That's what your slope is. Which we mentioned when we first came up with it over there.
Right.
Which we know what that is. So the negative of your slope is equal to f of y over f. The negative of your slope, because your slope is negative, so a negative times a negative, this is going to be a positive value. With me?
Yeah.
And now solve for f sub y. And so here's your f sub y. As a function of, notice that your partial of y with respect to x, we know what that is. That's some function in terms of x and t. So now here's your f sub y as a function in terms of x and t. Notice that this f is a constant. That doesn't change. The force that I'm doing up and down with, that's all over the place.
Right.
So the force I'm doing up and down, that's all over the place. That changes with x and t. But this f, this portion of it is always the same because we're not moving the rope one way or another. I'm not backing up and stretching out more that way as I go and moving forward. I'm staying here, just moving up and down.
Can we model that?
Huh?
Can we model that? Generating a wave and moving your rope.
We could, but we'd have to have a function for how we're moving back and forth. And then using that function, figure out what the tension is, and then we'd plug it in there. And just make it a lot nicer.
Cool.
Okay. And assuming that that somehow maintains this linear relationship, which I don't know now whether that would. I'd have to think about that.
Yeah.
Anyways, so here's how we now get f sub y. So we know our f sub y and we know our v sub y. So plug them in. So f sub y times v sub y. I'm dropping the fact, you know that that's a function in terms of x and t. I'm dropping the x and t notation on both those.
Yeah.
But this is the function in terms of x and t, and this is the function in terms of x and t.
We define what function multiplication is.
Yes, we already know that f times g of x is equal to f of x times g of x.
Okay.
All the way from, definitely did in calculus.
Yeah.
So yeah, we know what function multiplication means. Okay, anyways, what is f sub y? We already figured that out. That's negative f times the partial derivative of y with respect to x. And what is b sub y? We already know what that is. That's the partial derivative of y with respect to x. So now, let's just calculate the actual product. My f is right there. My partial derivative of y with respect to x, we have that written over here. Notice I'm just going to multiply. Here's my partial derivative of y with respect to t. Here's my partial derivative of y with respect to x. I'm just multiplying those two together.
Right.
So, this negative sign is going to be canceled out with the negative sign that comes from
Okay.
the partial derivative of y with respect to x.
Yeah.
The f is there. The k comes from the x1. The omega from the t1. The a, both of them had an a, so a squared. And both of them were a sine function in terms of same argument. Good? So this is flat out just that product. Remember, this f is just a constant. So nothing weird there.
Yep.
Good?
Yep.
And there it is. That gives you your power. That's a function of x and t. Pretty simple.
Yep.
Now, that's not the way we typically have it written. So before I do the substitution, let's mess with some variables. Reminder, velocity can be written as w over k. We did that derivation right under the velocity heading. We also did that velocity is a property of the system, kind of. It's also the square root of f over mu. That's the last thing that we did. So two different ways of writing the velocity. So those are both the velocity. Gonna solve for k. So bring the k over here and move this over there, which just flips a reciprocal. So when I move this over here, it's gonna flip the reciprocal.
Yep.
And I move my k over there.
Yep.
Good with that?
Mm-hmm.
And now just breaking the square roots up. Okay, so k is equal to this. And I'm going to make that substitution in for k right there.
Okay.
So when I make this substitution in for k, notice that we're going to have omega squared.
And K is our wave number?
K is your wave number.
Okay.
So substituting out my k with this gives me an omega squared. So omega and omega is where my omega squared comes from. Square root of mu, square root of mu. And now this square root of f cancels out with square root of f up here, leaving a square root of f in the numerator. You see that? We had a square root of f in the denominator. We had two square roots of f in the numerator, leaving one square root of f in the numerator.
Yep.
Okay, so this is the way that your book actually has the equation written.
So that's kind of a big thing.
Kind of a big equation, but notice it's all now in terms of k, omega, and then whatever your system was set up with. So we like when it's just k's and omegas showing up in the expression. I don't really see the value in the replacement from here to here, but there's got to be a use case for it because that's the way they have it written. Because you already had to figure out what your k was for your k there. So
Oh, yeah.
this one's just forcing you to introduce a mu. But then it also just helps give you more intuition, I guess, for what increases power. So if you're moving the wave the same way, but it's a denser rope, then that's going to increase the power, as long as you're doing the same movement. Similarly, same movement, but you increase the tension, that also increases the power. So maybe that's a good reason to do it, is just getting that kind of intuition. Good? Now, what is the max that your power then could possibly be?
When sine squared is equal to 1.
Yeah, when sine's 1, so sine squared is 1, and so here's your max power.
That's a pi halves.
Well, that's
That's
when
0.
this happens to evaluate to pi halves, or some multiple pi halves, or some odd multiple pi halves, because not pi. But pi halves, 3 pi halves, 5 pi halves, 7 pi halves. Okay. Now, what's your average power going to be? Well, I don't know if we ever did this derivation in calculus, but the average of the sine squared function over a full cycle is just 1/2.
It is?
Yeah. So sine squared goes between 0 and 1.
Yeah.
And then how would you calculate its average? You'd integrate under it. I don't think you know how to integrate the sine squared yet.
We don't.
Right? So you learn how to do that in Calc 2, I guess.
Yeah.
But you would integrate sine squared to get its area, and then divide by the area gives you, and then divide by the width gives you the average height. We talked about how to calculate an average height. So the average height turns out of sine squared is 1/2. So your average power is going to be 1/2 times your max power.
Cool.
Good?
Yeah.
Okay. So that's with power. Now let's talk about the intensity of your wave. Now, in a rope, assuming ideal circumstances, no friction, nothing like that, the intensity of the wave doesn't change as we go. But now if you think about a longitudinal wave like sound, intensity very much changes as you go. It's a huge difference if I talk to you right here versus if I'm talking right next to your ear. The intensity right next to your ear is much higher than the intensity from this far away. And so what's the relationship between that intensity and distance? We have intuition with these waves that travel out in 3 dimensions, right? If it's a 1-dimensional wave, intensity never dies down, it doesn't diminish. But now, sound is diminishing as it goes out.
Isn't it the square cube law? Or am I thinking of like light?
Oops. Squared. So intuitively, we think about intensity as the amount of power per unit of area.
Okay.
So imagine I've got some speaker right here playing sound. Well, if I go out some distance R1, first off, all the power that was emitted right here at the speaker, let's say a second later is how long it takes it to get to R1. Now that same power is spread out across that entire, remember this is a 3D picture, so entire sphere around the speaker. And so, the intensity at point 1, the intensity at R1, is just going to be whatever our power output of our speaker was, divided by the surface area of the sphere that it's reached so far. And surface area is just 4 pi r squared. Similarly, by the time it gets out R2, this distance, then the intensity is going to be the exact same power, but now just divided by its sphere that it's now spread out over.
The power doesn't change as through the wave.
Sorry, what?
The power doesn't change as you.
The power is the power we are using to emit the wave. Right? If my speaker is generating 10 joules per second, it's generating 10 joules per second. And so those 10 joules spread out more and more and more as the wave goes out, and the sound dies down.
That makes sense. Okay.
And so if I double my distance from you, then the intensity of the wave is 1/4 what it was.
Makes sense.
Now, it does make sense.
It
Might not make sense with your intuition, because if I stand 1 meter away from you, and then I go to 2 meters, my volume isn't 1/4 what it was.
No, that's not what you were saying.
Right? But the power is 1/4 what it was. The intensity is 1/4 what it was. And it's because our hearing isn't calibrated in this linear way. Our hearing, same with our sight, are calibrated in a more logarithmic way.
Right.
So for example, if I were to take this room completely pitch dark and I turn on 1 light bulb, that lights up the room. If I were to turn on another light bulb, that doesn't double the brightness of the room to our eyes, even though it doubles the amount of photons in the room. The room is twice as bright in terms of counting photons, but it doesn't appear twice as bright to our eyes in the way that we're calibrated to see things. Similarly, in the way we're calibrated to hear things. We hear and we see on a logarithmic scale. Very roughly speaking, in order for something to seem twice as loud, it really needs to be 10 times as intense. And for something to seem twice as bright, it really needs 10 times the intensity.
That's
Very roughly speaking.
Where are you getting 10 from?
Just because it's on a logarithmic scale. Maybe it's not 10.
It's about.
It could be 13 times is what it actually comes out to, or
I think
9 times.
decibels run on a 10 scale.
But we do it on a logarithmic scale. So it goes logarithmically, not linearly, is the point. Okay. So anyways, the point is, since it's always the exact same power that we're talking about, then I1 over I2, the ratio of your intensities, is going to be, well, when I2 is this. When you do a fraction divided by a fraction, you do a fraction times its reciprocal. Good with that?
Sorry, can you say it again?
So I1 is this fraction, I2 is this fraction. A fraction divided by a fraction is the top fraction times the reciprocal of the bottom fraction. Powers cancel out, the 4 pi's cancel out, leaving R1 over R2. And so this is called your, the book gives it some special name, something power law. They call it your inverse square law for intensity. But that's where it comes from.
Sweet.
Okay. Next thing we need to talk about is superposition.
What? It's not quantum mechanics term.
It shows up in quantum mechanics because waves show up in quantum mechanics. But superposition is our next major topic and our last real major topic of the section. Let's set up a thought experiment. So here you are, you're holding one end of a rope. The rope goes along, and here's a pole. And now as your rope goes along, it has a little metal circle that wraps around the pole.
Okay.
That wraps around the pole right there. And let's say that it can move in a completely frictionless way, up and down the pole. So now you have this rope, and you give it, a wiggle, and so you're going to send some wave down the rope, and it's going down the rope to there. Question is, so it goes down there, it's eventually going to raise this thing and make it drop. What's going to happen to the wave then? The energy has to go somewhere.
Back.
And the wave is going to bounce back towards you. Now question, when it bounces back towards you, what is it going to look like? Is it going to be up here at the top?
Reverse.
Or is it going to come down reversed at the bottom?
Reversed.
It would come reverse, wouldn't it? Not sure.
Well, think about it. As this travels and comes down, this thing's going to go up and down again, right? Which is like generating the exact same wave back towards you. And so it's going to stay up just like that.
Okay.
Good? On the other hand, let's say that we fix it. So now it's tied to the wall. So now it can't wiggle.
Oh, I thought it was like that.
No, before it was sliding up and down on a frictionless ring. Now it's tied to the wall. You send the wave down, what's going to happen?
Back.
The wall is just going to eat the wave.
Yeah, it's not gonna. What? Does it
Where does the energy go?
Back into the rope.
Oh, the energy has to come back into the rope. And so if I send a wave down to a rope that's inserted into a wall, can't move in any way, completely fixed,
No way, it's right.
then the wave is going to come back right at me.
It comes right
The energy has to go somewhere. If it can't leave the rope, it stays in the rope.
We're trying this. I don't believe you.
It's true.
Now the question is, how does the wave bounce back?
Reversed.
Reversed. So he's saying that the wave is going to come back, but now it's going to be down like this, traveling back towards you like that.
Why?
How can it just magically move down? That doesn't make any sense.
Because the force acting on it.
What force acting on it?
When you reach the end of the wall, then it flips down on you. Because it tries to go up and it can't go up, so it goes down.
Right. So as this wave reaches the wall, it can't move it up, and so the wall is creating a force downward on the wave.
Right, okay.
And so during the entire time that that wave is trying to escape, the wall is doing downward work on the wave. And so now that generates a downward wave back towards it.
Cool. Those waves interfere with each other as they go out.
If you send it back, then yes, these two waves can now interfere with each other. So let's say you send a wave, and then as it's coming back, you send an identical wave again. So now the question is, as these two waves meet each other, what's going to happen?
They should cancel out, right?
They're going to cancel each other out, and that is our principle of superposition. Our principle of superposition is that the wave equation that you would have for the sum of, for two waves, so say that this is wave y1 and this is wave y2, what's going to happen as they meet each other? The result is just simply going to be the algebraic sum of the two waves.
And this is what Apple uses, right?
And that is the superposition principle.
Yes.
In their ANC, active noise cancellation.
Yes, in noise cancellation, what's the big idea in noise cancellation? Here's roughly what it is. Well, let's keep a really simple idea of it. White noise machine. What does a white noise machine try to do?
Well, that one just
Create a bunch of random noise.
Creates a bunch of noise at a bunch of different frequencies, trying to cancel out just random frequencies that people might talk with
What? It doesn't count.
to create some sort of destructive interference.
I thought it just masked it, like kind of drowned the sound out.
No, it's trying to cancel out those frequencies. And
What
so
does that?
noise canceling headphones are trying to do a similar thing. When sound is coming in, they're trying to generate frequencies that would create destructive interference with
Which
whatever
is that.
it is you're saying.
Yeah.
Or whatever the surrounding noise is. And so, yes, it's using the superposition principle. Here's the incoming frequency. Figure out the frequency we need to generate to try and make this come out to just a zero wave. Try and perfectly cancel it out.
Right.
If the wave coming into your ear looks exactly like this, then the noise canceling headphone wants to generate a wave that looks exactly like that.
Well, the
So
problem
that perfectly cancels it out.
the problem they have is that the higher pitched frequencies move faster.
Well, this is a very difficult thing, but all the frequencies coming into your ear, it turns out, they can all just be added up in this exact same way. And so the result is just some wave equation.
But
Wait, but is it a wave equation that works like a regular sine wave, or?
So let's calculate what this wave equation would be now.
Okay.
So we're going to stick with, let's actually calculate by hand. And what we're going to do is we're going to calculate exactly what that equation would be for two waves interfering with each other. Now we're going to make two assumptions about the wave. Well, here's the simple case we're going to keep it in. We're going to keep it in the simple case that I'm just going to stand here. My rope is tied to some wall or something like that.
Yeah.
And I'm just going to keep generating the same frequency. And eventually, the wall is going to return it flipped back towards me. And so we're going to look at how those two combine. So that's a special case we're going to look at. Here's how you would do it for any two arbitrary cases. You want to know what the resultant wave looks like for two specific waves? Go ahead. A very interesting case that we care about is you keep generating one particular wave and then it starts coming back and interfering with itself. What does that look like?
Right.
So that's a special case that we care about, so we're going to calculate that exact case. You with me? So, we got the wave that we're sending on the top. It's going to go here and bounce back and come back this way. What's the difference between the wave I'm sending that way and the wave coming back at me?
they're flip signs.
One is that they're flipped. When this one's positive, this one's negative.
Yeah.
And the other difference is
Directions.
directions. This one's traveling this way and this one's traveling this way.
Yep.
So I'll use y1 for our wave going this way and y2 for our wave coming back. So if y1 is equal to, we'll just say that it's equal to a times cosine of kx minus omega t. So let's say our y1 is that, whatever the a and the k and the w are for this specific one, for omega. Then what is y2 going to be?
Same thing.
One, it's flipped from it, so it's going to start out with a negative sign. And it's going to be a times cosine of kx plus omega t. Why plus omega t? That's related to the velocity. Notice that going all the way back when we first had our velocity, flipping the sign of the velocity would have made that a plus, and then everything's just a plus.
Yeah.
So that's ultimately capturing the fact that the velocity is going the opposite way.
Okay.
Okay, so now let's calculate our resultant wave, y. What is y going to be then?
Let's do that together.
It's just going to be the sum of these two things.
Is it 0? Almost. Wait, no, it's not quite 0.
It would be 0 if they're the same wave. What was the initial question?
This is not going to be 0.
It would be if the A's were
No.
A's and X's and K's and
Yeah, they're not the
Omegas.
same. They're not the same.
Very different.
They
They're
equal
traveling
0.
together.
If they were both waves that were exactly opposite amplitude and both traveling in the same direction, then yes, they would always cancel out. But now it's going, interfering, and coming back the other way.
So you're saying when they meet, then
You are thinking about if we had this. What would that scenario look like? That would look like I'm generating one wave that looks like this, going that way, and then in the exact same place, in the exact same direction, I'm generating this wave.
it's
And yes, in that case, then it would be exactly 0. But we don't have that. I'm sending the wave down, and then it's bouncing back, coming back at me.
and you send one.
While I keep on generating the wave. I hook up some spring, some mass on a spring generating the wave. There it goes. Eventually the wave hits the wall and starts coming back. And now that's going to create the new resultant pattern, where the wave is interfering with itself. We're figuring out what that pattern is.
You're saying it won't interfere. It will just keep on.
It's going to interfere with itself. It's just not always just going to be zero.
If it's the same A and same omega and same K, then what is it?
It's not just, let's calculate exactly what it is, but it's not coming out zero.
Okay.
Notice that this is not just a negative of this, because these are different. Look, cosine of pi thirds plus pi thirds is not just the negative of negative cosine of pi thirds minus pi thirds. The fact that there's a minus in there makes these very different things. They're not just canceling each other out. So the negative of that is not just equal to the negative of that. This one is a cosine of pi 6. This one is a cosine of 0. Those are very different things.
Okay.
So the fact that there's a plus there and a minus there, huge.
Huge.
Now, if there was a plus there and a plus there, okay, now those are equal to each other.
Yeah.
Okay. So completely different. Good. All right, so let's actually calculate this thing. Sorry, I don't know why I'm erasing. So this is equal to, let's see, some trig. I know you guys all have this memorized. What is the cosine of alpha plus beta?
Alpha plus beta 1. Oh,
What?
no.
What's our trig identity for alpha plus beta? And then we'll do the minus after.
Sine
Cosine of alpha times cosine of beta,
plus
plus or minus sine of alpha, sine of beta.
I was saying that.
Alright, and we derived that at the beginning of calculus. If you don't remember, one of our trig identities.
It's a big circle and all triangles.
Yep. That was one of our more complicated ones that all the other trig identities kind of followed out from, the ones that didn't just fall from the Pythagorean theorem. Okay, anyway, so we're going to apply that to this. Let's factor out the a's from both. So here's the a.
Okay.
So now writing this portion, plugging into that, what is that going to be? That is going to be the cosine of alpha times the cosine of beta minus the sine of alpha. Sorry.
Right,
That's right,
using the
alpha.
trig identity. Solve it.
I'm adding these two things together.
Well, that's not cosine
Okay, but
of alpha plus beta. That's cosine of alpha plus cosine of beta. Isn't it?
I'm expanding this one. Sorry, so far I'm just
Oh.
expanding this term.
Oh, okay.
So
Oh.
cosine of alpha, cosine of alpha, cosine of beta, minus, since it's a minus sign, sine of alpha times sine of beta, and that we expanded out y1. Now I'm going to expand out y2. Notice y2 has our negative sign here. So I'm going to do a negative of whatever we write. So we're going to have minus cosine of alpha times cosine of beta, minus again, it would be plus, but this minus sign needs distributed to it. So minus sine of alpha, I wrote beta, omega t's are beta, minus sine of alpha, alpha is kx, times sine of beta, beta is omega t. Okay, there we go. Did I do everything correct?
kx,
Good math from.
kx.
I did everything correct, except for these ones were the ones that had the negative sign. So, you were supposed to be negative. You were supposed to be negative.
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 Positive.
And then this one should be positive.
Negative.
Wait, that was
And
your
then
y.
negative. Okay.
What?
That was your y1 term, though, wasn't it?
Oh, wait.
The first four were your
Still
y.
messing up.
The first
Let's
one should be
do
positive.
this correctly. No, this was my y1. Why am I getting so confused?
So you had it right the first time.
Back to the beginning. Alright. Cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Did you do that correctly?
No, it should be plus, but wait, isn't beta negative though? For y1, isn't beta negative? Shouldn't it be plus sine of kx times sine of omega?
Or minus sine of alpha, sine of beta. So we have a minus sign here.
Why is that minus not plus?
When you subtract the angles, then you subtract
The sine. Okay.
the sign.
Got it.
And then the one to the right of that
Okay.
should be a minus, right?
So now, U should be a minus, and then U should be a plus.
Mm.
No, you should
No,
also
you
be a
should
minus.
minus.
Okay. If we did this correctly, the cosines should cancel out with the cosines, and the sines should stack up on each other.
Yep.
Which they do. Okay, good. We did correct. U cancel out with U. We're here. And then we have a negative sign for a total of -2 sine.
Okay.
So this is equal to -2a times the sine of kx times the sine of omega t. There's our new wave, where here's our amplitude. Amplitude of -2 and amplitude of 2 mean one and the same thing.
Of course it just doubles.
Well, it doubles the sine, it cancels out the cosine.
What does that even mean?
That makes so much sense.
But the max amplitude is twice as big as the amplitude of each of the individual waves,
so
which we would expect when they add together perfectly.
So what does that drawing look like then?
What does this drawing look like?
a heap big wave
So,
and then no wave.
what this is going to look like is drawing it at different times once you get it going.
Okay.
One potential way it could look.
What?
So,
Depending on the RMG of the computer.
so here's what it could look like at its max displacements. A second later, it might look something like,
Is this after they combine?
yeah, so this is, I've been going for a while.
Okay.
All right, and we got it all said and done. It's hooked to the wall, so that's going to be a generating point, and my movement will assume that the movement of my hand is small compared to the waves we're generating, so that's basically a fixed point. So it might look like this. At a later second, this might come down, and that might go up some. At a later second, something like this,
So it does go to 0.
and then it will eventually have a point where it looks exactly straight, and then like this, and then like this, etc., until we get our max displacement the other way. And so this, the generation here, the amplitude of the new wave will be twice as big as the amplitude of the wave I generated in getting it to bounce back and forth.
Makes sense. Okay.
What is that?
There will be these points on the function that never move, which is the interesting part. So here's one potential picture. The other potential picture could have been something like where there's a bunch of these points that never move. And so then at a particular time, it might have looked something like this. Now we're going to quickly see from our derivation that there's going to be points that never move.
Okay.
Notice that this is always changing with time,
True.
but your position, once you have your position on the function, that's your position on the function. There's going to be certain positions that make this always 0.
Oh, because sine of that is 0.
Yeah. So let's really quick write out this equation. He uses I can't remember what variable he uses for the amplitude.
I think it's A, isn't it?
It's A with a subscript,
Oh.
SW, for a standing wave. Okay, it creates what we call a standing wave because it stops looking like the wave is moving back and forth anymore, and instead it just looks like the wave is changing positions right there as you're watching it. And it stops looking like a back and forth wave, so that's why he calls it a standing wave. And so he does ASW for standing wave. So the Y we get when we have this interference, and it's a Y in terms of X and T, maybe just make that explicit, is going to be your new amplitude, which is twice as big as the amplitude of the waves you used to construct it, times the sine of Kx times the sine of omega t. Okay, so there is our standing wave equation. Once you get this interference of a wave with itself, with some fixed endpoint. Good so far?
Yep.
Now notice that if Kx is a multiple of pi, this whole thing is 0.
Yeah.
So whenever K times X is equal to some multiple of pi, then this whole thing is 0.
What does a multiple of pi even mean?
Meaning it's a natural number
Meaning
and it's a natural number.
you can divide it by a number and get pi.
Let's say that our wave number happens to be 1, and you are standing exactly 3.14159 meters away from where it started.
Oh, I see. So just if both
Then-
of those numbers come out to pi.
If both those numbers come out to pi, or 2 pi, or 3 pi, or 4 pi, or 5 pi,
I need multiple.
and being some whole number here.
Yeah.
Some natural number.
I see.
You good?
Yeah.
Okay, so that's going to be when x is equal to some integer multiple of pi over k. What is k?
So what number?
It's our wave number, which is 2
2
pi over
wavelength.
Lambda.
wavelength. So put the 2 pi down here and the lambda upstairs. So this is n times
3 pi?
pi times, put the lambda upstairs and the 2 pi downstairs,
Wow.
which is equal to n times
Pi over
lambda over 2,
Uh.
where lambda is your wavelength.
Yeah.
So, if I generate some standing wave, then every half a wavelength, I will have one of these positions that doesn't move. We call those nodes. And now that makes perfect sense. Here's one, go half a wavelength. There's one, go half a wavelength. There's one, here's half a wavelength. There's one, here's half a wavelength. There's the end of our wave. And so it has to be multiples of half wavelengths. Then we find these nodes, these points that never look like they're moving. They always look like they're just standing still. That make sense? So, with that, let's just talk now for just a second about an instrument. So you got an instrument string of some length L. Violin string or whatever string, some string on some instrument. Now it's fixed on both these ends. So any standing wave you generate on it has to have these as nodes.
Yeah. Right.
So what is the biggest wavelength you could possibly have on this thing? So our length here has to be equal to some number of pi, or of lambda halves.
Okay.
Because our endpoint here has to be one of the nodes. And our nodes come every lambda halves.
Yeah.
Right?
Okay.
So maybe we had a lambda halves here, 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 and there. In that case, it was 4 multiples of lambda halves. Right?
Yeah.
So what is the biggest wavelength we could possibly generate on that string?
L.
That would be when n is equal to 1.
Yeah.
When n is equal to 1, what is our wavelength?
L
2L.
2L.
Our wavelength is 2L. In other words, we could have that string. Notice if this string just went like this. If it went just like this, doom, and then went like this, straight, went like that, and then went like that, it's only generating half the wave at a time. So that is the biggest wavelength we could possibly have on that string, is half of it. Half a wavelength. Here's the biggest our wavelength can be using that string, is a better way to say it.
Okay.
Using that string, what's the biggest wavelength we can get? That. And so we'll call that wavelength lambda sub 1. What's the biggest frequency we can get on that wavelength, or on that length then? So,
Why does that matter? Why does frequency matter?
velocity is equal to frequency times lambda, right?
Correct.
And so,
V over lambda.
the velocity on the string is going to be fixed by whatever the string is that you have there. And so, it's going to be equal to what?
Lambda equals velocity.
Lambda 1, we substitute in. What's our frequency going to be?
Velocity over lambda.
Our frequency is just going to be velocity, v, over lambda 1. And we'll call that the lowest frequency you could possibly get.
Lowest. Or highest.
The bigger your wavelength, the smaller your frequency.
Oh.
And we could write this as, what was our frequency here for lambda 1?
2L.
Just 2L. So this would be v over 2L. what other frequency could you have? You could have one for every possible lambda that we could have. So if we call this L sub n now,
Infinite.
yeah, but let's write out what exactly they are. And so,
Between.
what are all the lambdas that I could possibly have then? What are all the valid wavelengths I could have? So lambda sub n, for each n, what wavelength could we have?
Square bracket.
We could have 2L over n. Those are all our possible wavelengths that we could have on that string. So we could have a wavelength of 2L, that's plugging in 1.
N could be any number.
We could have a wavelength of just L, that would be a standing wave that looked like this. We could have a wavelength of 2/3 L, that would be one that went like this.
We got 6.
So we got 1, and then a half left, or 3 halves, I guess.
You do 6.
Yeah, we could.
Yeah, you could do 6. You could do any number that you, and plug in any n you want here, and that is a valid wavelength you could get
So
using that string. And since those are the only wavelengths you can get, what are the only frequencies you can get? So then F sub n is equal to V divided by lambda, or times the reciprocal of lambda, n over 2L. You with me? Now, we can rewrite this as n times V over 2L, but V over 2L is just your basic frequency. And so every frequency you can get is some integer multiple of what is called the base frequency of that string. And so when you have some guitar string, it can only generate certain frequencies.
based on.
And so it can do the base frequency and integer multiples of that same base frequency.
This is what the frets are for?
Huh?
Is that what the frets are for? Am I thinking about the
What the,
frets on the,
I'm not sure what a fret is.
like the places you put your finger on the guitar?
Oh, so now let's look at what would pushing down on one of those do? It would shorten the length,
Yeah.
which would change the available frequencies from that string.
To a slider.
Yeah. High pitch.
Yes, the longer the string,
The deeper the note.
the bigger the wavelength, the lower the frequency, the lower the note sounds. That's what I mean by low sounding voices, low sounding notes.
Yeah.
They have low frequencies. High being high pitch, being high frequencies. Good?
Yeah.
And now notice one more thing. Velocity comes up, our F1. Our F1 was calculated this way. So, making a longer length, what does that do to our frequency? Bigger length does what to our frequency?
Bigger length, bigger frequency.
Lowers the frequency.
Lower.
Makes it deeper, which you have intuition for. But now notice you also have this V. So we'll do the 1 over 2L, but let's rewrite our V. What is our V as a property of the system we set up? It's a square root of F over mu. And so those are two other things that your guitar, you'll notice, has. The strings have varying densities, which change the velocities of the string, which then change the base. Perfect. And then when you're tuning it, you're tightening it, changing the F.
Does it matter?
Getting that right frequency that you want.
Cool.
Does the medium matter because you have like steel strings or synthetic?
I'm guessing, well, look at, here's what matters.
Mu. Yeah.
The density.
The density matters.
The density.
It doesn't care what your string's made out of, it cares the density of your string.
So
Now, I'm sure that there's also probably some reasons that the material matters that we
Percent.
probably looked over, but it's probably insignificant compared to these other things.
Really?
I'm guessing, I have no clue. Maybe there's some fine tuning that actually, it turns out that matters. Remember, we're ignoring air resistance.
That just
We're
doesn't
doing
seem
the
right.
equivalent of ignoring air resistance. So, I don't know, I'm not a guitar expert. But I'm guessing it's insignificant compared to the density, and the density is what really matters.
The material will give you density, I think.
The
Yeah.
material is largely going to matter to make sure that you can apply the tension that you want,
Yes.
so you don't break it. You can't create a guitar out of, I guess you can create a guitar out of rubber bands, but but if you try and do the same tension, you're going to break that rubber band.
What about like,
So
that just doesn't seem right.
the tension and the thickness and the length give you your base frequency. And then if it's a standing wave, you can only get integer multiples of that same frequency. And so instruments can give you relatively reliable sounds repeatedly, and that's why. Good?
Yep.
Okay. Should we see if we can get through a couple more examples? That ends lecture material at least.
Hey, you didn't think we could do this?
Nope, I didn't. Okay. Let's go back to our power example. It's going to use the numbers from example 2. In that example, at what maximum rate does Thraki put energy into the clothesline? So they want to calculate the max energy here.
So do we have our mu?
So,
What's it mean?
Calculate.
let's see. That is, what is his maximum instantaneous power? The linear mass density of the clothesline, okay, they give us mu. So they tell us mu is 0.25. So our mu is equal to 0.25.
Sweet.
Times our force.
And the tension they give us, F, is equal to 36.0 newtons.
So
This is also 3 significant figures.
2 pi f and then times our a, which our a is.
So it's 2 pi times 2.
Okay, so
What's our f frequency?
we already have our
Oh,
amplitude.
So
I don't even know if it's worth plugging in.
it's just plug and chug.
Yeah, it's just plug and chug. So you have that. Our omega we have over there.
Yeah.
It's 4 pi.
Yeah.
And our amplitude we have over there is 0.075.
Omega is 2 pi times
2.
frequency.
So if you plug that all into this, then you
Which
should
is
get 2.66 watts.
6.
So P max is
Wait,
2.66.
How does the unit watt come out of this?
Watt is energy per time. So power is in terms of watts.
Yeah.
So this spits out watts.
No, power's in terms
This
of
spits out
joules, right?
No, power is joules per second. That's what a watt is.
Yeah.
A watt is a joule per
Oh,
second.
so it's the same thing.
Work.
Energy is a joule.
How does it work?
Position is meters. Velocity is meters per second. Energy is joules. Power is joules per second.
And what are joules?
Work.
Energy.
Well, what's there? They break down to either.
Oh, that's what you're saying? How do you get it? You get a force
Over time?
times a meter. If you want it in Newton meters, that's one way you can have it. A Newton, how do you calculate that? That's mass times acceleration. Sorry, that's M per meters. So this is a mass times acceleration, so that would be kilogram meters. Then we got that meters gets us meters squared per second squared, and there you go. There's your units of joules.
And that doesn't.
And you
make
want
any
watts? There's your watts.
sense. A watt. It moves. It moves
Okay,
5.
sweet.
I don't know.
Okay, so you can just plug and chug into that. Nothing interesting there. Example with the inverse square law. A siren on a tall pole radiates sound waves uniformly in all directions. So,
Up here at our eye.
yeah. This is also just going to give you an intensity and a radius and another radius or another intensity and have you solve for the last one.
Well, if it's all there, we can just.
Yeah, so we got our pole here and it's emitting sounds. Da, 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 da. Okay. Siren radiates all directions at a distance R1 equal to 15 meters. Then it has an intensity of I1 is equal to 0.25 watts per meter squared. At what distance is the intensity equal to 0.01?
Just.
And so you just need to find the R1 that does that,
So it's
or R2
4 pi times.
is what we're looking for.
Times I.
So R2 is going to equal R1 times the square root of I1 over I2. Just from
From what?
this equation.
Oh.
Solving for R2. So put the R1 over there and then take the square root. When you take the square root of the R1 squared, that's just the R1. And then just the square root of that
So
fraction.
what are those other ones above that? That's what I was looking at.
Oh, these?
Yeah.
That's how you calculate intensity from power. If you know your power and you know your radius, you can get your intensity. This already gave us the intensity at both points.
Oh, I thought we were solving for power.
Oh, we could solve for power if we wanted to, but not what they asked us to do.
Okay.
Okay. Kind of about time. Should we try and do one more? Let's try and do one that has superposition. Okay, a guitar string lies along the x-axis with an when in equilibrium. The end of the string is at x. The end of the string at x equal to 0 is fixed. And then they give us an amplitude, they give us a frequency, da 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 da. So basically, they're going to give us information, and they want us to populate this equation. Remember that this is going to be the equation you use for something like on a guitar string. Because you're going to send a wave down it, and then it's going to bounce back, and now it's going to go back and forth on that string. So here's the equation that you would use in this equation, or in this problem, and they're just giving you the various numbers. They're telling you what the amplitude was, they're telling you what the frequency was, they're telling you what the velocity was, and so you just have to find the values and then plug it in. So it's going to be very similar to the example we did coming up with the wave in example 2, except for using this equation rather than that equation. So it just switches your wave equation.
Is the homework that easy too?
I don't know. I don't have that kind of teacher. So maybe just stress that point. Don't get that confused when you're doing your homework problems. If you're generating a wave, then it's going to be that equation. If it's something like a guitar string where the wave's going to go back and forth and interfere with itself, you're going to use this equation. And I think that those will be the only two wave equations that you really have to use.
Well, they asked you to do what you did over there.
Okay, so hopefully we're good with that. Sorry. Glad we got through it today, though.